Yeah, I wish I was today.
So far. You still want more seat. No, perfect, perfect. It's interesting because this morning the first talk was fine, the second talk was cut off at the corner.
Yeah.
And then this talk was like this.
So it must.
I guess it's the aspect ratio.
Yeah, it's something. How different. Here's a different ratio.
You must have had a long flight. Yes and no. Okay.
Yes, because I came on Saturday night.
So good afternoon. Let's start our afternoon session. It's my really great pleasure to introduce our first speaker of this afternoon, Professor Sabrina Streipert, and she today will talk about Beverton-Holt model on time scales and its application. Thank you very much, Sabrina.
Yeah, of course I want to say something. So, Sabrina is one of my PhD students, very successful one, with a big, big future in front of her. And we met at a party. And I told her to come to America, and she came. This was in Germany,
Yeah, thank you very much. Yeah, it's a real honor to be here. And yes, it was a Christmas party. And I actually thought that Martin Bohner is a student, so I asked him, how do you like your courses? And he said, good, I'm the teacher. So yeah, that's how it all started, and then exchange program, and then I was a waitress, and then I came back. Anyway, so yeah. So anyway, so this feels like a homage to my previous supervisor, to my PhD doctor father, Martin Bohner, because this is a topic that has been accompanying us throughout the years, and we kind of sucked in Jacqueline, and Tom got sucked in a little bit too. So yeah, I will enjoy, and I hope so do you. Yeah. Okay. So Raymond Beverton and Sidney Holt are two fishery scientists who in 1957 published a book on exploited fish dynamics. And in that book occurs that recurrence that we see here on top. I'm going to talk about this, and it coined the name as Beverton-Holt model. And the way it was derived is actually they started out with a logistic growth model, continuous time, and we're going to assume R to be greater than 0 because otherwise the population goes extinct. And they go ahead and write like we're going to get the explicit solution. One way of doing this is to do the transformation 1 over x, and then it's linear, non-homogeneous, and we're going to solve it. And then we're going to resubstitute, right? And of course you have to first show that solutions to positive initial conditions remain positive so that the transformation is well defined. Anyway, you're going to end up with this explicit solution. Doesn't have anything to do with the recurrence yet. I'm just going to copy paste that. And now the idea is to say, well, we can express the solution at time t naught plus capital T in this form, right? Just replace t with t naught plus capital T. And now we can say that capital T is a generation time. And so that means that x evaluated at t naught plus capital T is the new generation, which is then denoted by yt plus 1, and the population at time t naught is the previous generation, and t naught was arbitrary anyway. But this is how they basically derived their recurrence. That is now the Beverton-Holt model. And as you can see in that recurrence, there occurs this e to the negative rt. You're going to multiply this throughout. And so this guy is our rho that appears up here in the top. And so you notice that this rho is bigger than 1 because we have e to the rt, okay? And so if you were to choose rho to be, if you just look at this recurrence without remembering the derivation procedure, then it will result in negative solutions, or it can result, right? So that's just something to keep in mind, that we really should remember how it was derived, and if you do so, then you remember rho must be bigger than 1 for this to be well defined. Anyway, now we can, right, and then you can show that solutions remain non-negative for non-negative initial conditions, all right? I mean, we have an explicit, we can solve it explicitly, right? And not only that, but the solutions behave, and you can prove this, you can even get an explicit solution again of this recurrence, but you can show that solutions to this recurrence converge monotonically to this carrying capacity K. And that's the same dynamic that we know from the logistic model. And that's not a surprise, because it's really like a Poincaré map, if you think about, right? Like you just evaluate the points at particular time points, but it's really an underlying logistic model. Anyway, so as I said, like it comes maybe to no surprise, especially since it used the logistic model in its derivation, that it has the same dynamics that we know from the logistic growth model, where we converge monotonically to that carrying capacity. And that was proposed by Pierre-François Verhulst a long time ago, and it's now being used in all kinds of bigger models, epidemic models, multi-species models as building block. Anyway, so here just to summarize, we see on the right the logistic growth model in continuous time and the Beverton-Holt model on the left. Both of them can be solved explicitly using a transformation of 1 over y, and the dynamics are exactly the same for positive initial conditions. You're going to get that monotone convergence, again remembering that rho must be bigger than 1. And this is why oftentimes the Beverton-Holt model is considered as a discrete analog of the logistic growth model. It's not really the logistic map that one may think of, right? That exhibits potentially chaotic behavior depending on the parameter values. Anyway, and again, it shouldn't come to that much of a surprise because it used that logistic model, right? Now, we have it here as a recurrence, right? And I mean, the goal, as we learned already in many talks before, is to do this all on timescales. And so the first step would be to translate or to rewrite this as a difference equation, right? So, and I'm gonna, this is not my invention, I'm gonna follow the same outline as a paper before me by Howard Worth and Martin Bohner from 2007. So the idea is to start dividing by rho. And you get 1 over rho, rho minus 1 over rho. You introduce rho minus 1 over rho as alpha. Rho is bigger than 1, so alpha is between 0 and 1. Now you're going to cross multiply this term from the left to, from the right denominator to the left. And you notice already a k yt plus 1 and a k yt. So, right, what do? We move that from the right to the left, everything else to the right. So that we can express that as a k times the forward operator, all right? And then we just divide by k, and we end up with this difference equation that is representing the Beverton-Holt model. Even if it may look weird because there's a yt plus 1, that's no problem, right? Like it is from the actual Beverton-Holt model that is completely well defined, okay? Now I'm gonna copy this. This is for difference equations. And now the idea was probably, I mean, I can only assume, that in order to do this on time scales, right, you know, the derivative turns into a delta derivative and the t plus 1 to a sigma. And so I suspect that this is how the Weber-Holt model was motivated. And you can see that if you choose the time domain to be real, your delta derivative turns to a normal derivative and the sigma is just y. So you end up with the logistic model, and in the discrete case you're going to end up with your Weber-Holt model, right? That's just the difference equations form of the Weber-Holt model. All right. Now, I should make a note that I talked a little bit about its relation to the logistic model, right? Now in timescales we have also a very nice relation to the logistic model that was introduced by Martin Bohner and Elban in 2003. You can also find this in their second book. Very short paragraph where they talk about or introduce two different classes of logistic models. The left one and the right one, and they very briefly describe but show in the paper of Elban, Aiken, Bohner, and Bohner, they go through the derivation and get the explicit solution for either of these forms. Now I marked this one, and the reason for this is that our Weber-Holt model can be expressed in exactly that form as on the left-hand side. Okay? Just a side note, I guess. So it's a special case of that logistic class. And just a note, there's a paper by Delphine Torres and Maria Lemos Silva that introduces or expresses the logistic model slightly different, but that's also just a special case of what already appeared earlier, right? Can just be rewritten in that way. Anyway, so let's get to the applications, and I'm going to focus on one particular one, and that's where there are tons, but I'm going to focus on the Cushing-Henson conjectures, my favorite. Started out in my PhD and kind of, yeah.
Followed all your life.
Yeah, I mean, yeah, nightmares but hopefully we soon have it solved anyway, so then it may disappear soon anyway. No, but it's fun, right? So I should say Cushing and Henson, Jim Cushing and Chandel Henson, they used experimental data from flower beetles to investigate the impact of periodic environments. And what they noticed is the population followed the Weber-Holt type model, or they used that Weber-Holt type model to express the growth of the population. And then they started changing the environment K. So that K is now time periodic. And what they found is, they conjectured and they showed it for omega equals 2, that there's a unique omega periodic solution that is a global attractor for positive initial conditions. And probably, if not more exciting, but certainly at least exciting, is that the introduction of this periodic environment is deleterious to the population. In the sense that on average, right, like now you have your unique omega periodic solution, it's globally attractive, so we basically just look at this omega periodic solution, and on average over that period, it's going to be less than or equal to that average of the carrying capacities. And why deleterious? Because it's only equal if K is one periodic, which means in the discrete case it's constant, right? And so this is exactly what the idea is, that in the constant case, if it's, you get equality, otherwise it's less. And then there were many different people who approached that and tried to prove the conjectures and did so in different ways. One of those ways was then by, not surprisingly of course, Martin Bohner and Howard Worth, and they even formulated this for the timescales version. So we see here our Weber-Holt model, right, on the dynamic case. And we have that alpha, minus alpha is in R plus, that basically ensures that we have non-negative or positive solutions. And my K is omega periodic, and I get to this. KT plus omega is equal to KT. And then you can guarantee the existence of a unique omega periodic solution that is globally attractive for positive initial conditions. So this is the first Cushing-Hansen conjecture, and they proved it very nicely, right? Using Jensen inequality. And then well, not here. On this one. The second Cushing-Hansen conjecture, they were able to show that on average, that omega periodic solution integrated, right, over its period is less than or equal to the average of the carrying capacities with equality if and only if the K is one periodic. All right. Now that should ring a few alarm bells, right? And the reason for this is that I'm writing KT plus omega equals KT. And so on a general time scale, well, who knows if T plus omega is indeed in the time domain, right? So one of the assumptions was that T is omega periodic, meaning that T plus or minus omega is in the time scale. And this is a very common assumption in some other works where timescale models have been considered with periodic coefficients, and I'm listing only a few, and yeah, if you know of anyone else I should list, I don't want to step on anyone's feet, let me know. And some authors call it almost periodic, okay, almost periodic timescales. But that was basically, you know, a huge achievement. It's still relevant, but it's also restrictive, right, to require the time domain to be periodic. And so what about quantum timescales? That's not periodic, or any other type of isolated timescale, isolated points, right? Or even worse, maybe some union of intervals with isolated points, or whatever you can cook up, right? That's not periodic. And so that motivated us to think a bit more about periodicity, and this is where we kind of sucked in Jacqueline, I guess. And we started defining periodicity on timescales, or it started the journey to define periodicity on timescales. And so let me give you the idea, right? Okay. So I start with isolated timescales because I walk you through the journey, right? So we are now, I already passed my PhD, I'm now in my postdoc, and I attend Bedlevo, and Martin talks about periodicity and says this is an open problem, and we all sat together and thought about it and had an exciting time, I guess. So classically, right, we would think that if I just look at those points, this is a 3-periodic function, and the reason for this is that these function values are repeating. Now, we can equivalently think about this, that the area is repeating, correct? We have equidistant points, and so the length of a rectangle is just 1. Now, the way that these areas, or the equivalence of these areas, or thinking about them, allows us to generalize this to isolated timescales. Now the points don't have to be equidistant, but we can still talk about the areas being the same and repeating. So we would have here a 2-periodic function, because we say that the area of that rectangle that is constructed by the height, which is the function value, and the distance to the next point, to the subsequent point, is repeating. And so
some of these areas over one period is repeating, right? Not in
each of them is repeating, and when you sum them up, it's repeating. That is our integral invariance. Yeah, exactly. Yeah, but each of those, so this would be a 2-periodic function on this isolated time domain. And so we were able to then publish this in 2022, where maybe I start actually with the equivalent formulation, because this is where you see very nicely that area repeating, right? We have mu times f, that's the area of our rectangle, and that is repeating after omega time steps. That's sigma omega t. We are in an isolated time domain. Now, here's the importance, because we can equivalently write this in a way that will allow us to generalize this beyond isolated timescales, right? And so equivalently, we can write this as nu delta f nu equals f, where nu is sigma omega, okay? And so you already see that there's no mu appearing, right? If you want to generalize this to any time scale, mu could be 0, you get 0 equals 0. That's not useful. But the top will be useful. All right. Anyway, so if you choose the time domain to be integers, and I gave it a subindex I to indicate we are in the isolated time domain for now. If you choose the integers, they are equidistant, so mu is just 1. And if you look at this identity, we have mu f equals mu sigma f. Mu is 1, so on the left is f. Mu of sigma is also just 1. It's 1 everywhere. And sigma omega is the omega of next time step, that's just t plus omega. So we end up with a very classical periodicity definition, right? Now, but we now can choose, for example, the quantum time domain. And now mu t is q minus 1t. We again see here the identity of those equivalences in the area. And so just plugging that in, we have q minus 1t ft. And on the right, q minus 1 q omega t f q omega t. So the q minus 1 t's cancel, and we get that ft has to be q omega t f q omega t. And that's exactly the same definition that Martin Bohner already used with another PhD student, Rojana, right? Yeah, Rojana, in 2013. Okay. And just a side note, even if you're not interested in applications, this may be pretty useful, that the periodicity class is closed under circle plus, circle minus, scalar multiplication, and traditional addition and subtraction. Here we see what you just referred to, the invariance of the integrals. So if we integrate over one period, it's just repeating. Doesn't matter where we start, right? Very classically from what we know about periodic functions. And then something that I find pretty useful is also that we proved this first for one periodic, and then with Tom and Martin, we had another paper where we used this for any omega period. So basically any omega periodic function can be written as some constant over mu t, but this constant in the numerator is basically repeating, right? So you have a sequence of points as your constants in the numerator. And if it's just one periodic, it's a constant over mu. And that's extremely useful, I think. Anyway, but what it also allowed us is to now formulate the Cushing-Hansen conjectures for this isolated time domain. So we see here our Beverton-Holt model, right? We assume the time domain to be isolated, so we really can use a sigma, and rho is bigger than 1. Now, instead of classically you assume let rho be omega periodic and k be omega periodic to have a unique omega periodic solution. Now we have to adjust this slightly. So it's not that rho is omega periodic, but rather sigma delta rho to this nu is equal to sigma delta rho, okay? So in the discrete case, sigma delta is just 1. So you get rho to the nu, which is just rho evaluated at the omega's next time step, has to be equal to rho of t. That's traditional periodicity, right? And then the next one is that not just k has to be omega periodic, but k over rho minus 1 has to be omega periodic, all right? And again, if you choose the time domain to be the integers, that's just your classical definition of periodicity. The first one gives you rho has to be omega periodic, so that means k has to be omega periodic, right? And now what we have is, if we make those two assumptions, we can show that if that lambda is not 0, we're going to get a unique omega periodic solution. We can write it down explicitly. And we can even show that it is a global attractor for positive initial conditions, right? If we additionally assume that this integral is unbounded, and but the supremum of decays over the period are bounded. All right. So this is our first Cushing-Hansen conjecture on isolated time domains, right? So already interesting, but you know, if you want to study the actual application for species, then probably this is exciting, right? So we want to know, how does the population do when we introduce a periodic environment where the period is now that new periodicity definition, right? That allows us to talk about periodicity on timescales, isolated timescales. So in this case, right, traditionally we say rho has to be constant, k is omega periodic, then the average of the omega periodic solution is less than or equal to the average of the carrying capacities. So now the equivalence of rho being constant is now that sigma delta rho is constant. Okay, sigma delta is 1 in the integer case. Okay, and we assume A2 that was k over rho minus 1 is omega periodic in our new sense. And so if we assume that there exists, right, this lambda should be not 0, so that we do get a unique omega periodic solution, then we can show that if we integrate over one period, it's now sigma t naught, nu t naught, right, sigma omega t naught, then this is less than or equal, it's not the average of the case. It's 1 minus c, so it's like a weighted average, okay? But what you notice is if you are in the integer case, okay? So maybe completely obvious, but in the integer case, this is just 1, yeah? If your t is set. So now you have, your weight is 1 minus c, sigma delta, that's just 1 over sigma delta minus c.
No, 1 minus sigma delta.
Yeah, 1 minus.
What did you say?
Yeah, sigma delta, gladly, that's just 1. Okay, thanks. So right, this cancels out and you get traditionally your average of the carrying capacities. But what it also shows you, okay, so C is 1 over sigma delta rho, okay? So I maybe now, okay, now quickly, okay? So we have 1 minus C over 1 minus sigma delta C, okay, that's my weight. Now I'm just gonna, hopefully I'm not making a mistake, just plug this quickly in, okay? So from 1 over sigma delta rho over 1 minus rho, because the sigma delta cancels, okay? And so what you notice, right, you get, okay, sigma delta rho minus 1 over sigma delta rho 1 minus rho. So you already notice that you're gonna, if your sigma delta is bigger than 1, then you can already get a problem that your right-hand side is gonna be smaller than your actual carrying capacity. So the point is that it's certainly gonna depend on your time domain. Okay, so it may actually be beneficial for the population if you introduce such a periodic environment. All right. Okay. Now, okay. So now, okay, now comes maybe the most important part actually.
Going big to hard.
Exactly. Right. So we already heard a talk by Roman where the discrete motivated the continuous, sometimes continuous motivated discrete. So it was the same here. We did something for the isolated timescale, and that motivated us in order to define it for general timescales to first look into what happens in the reals. So this isolated timescale motivated some new theory in the reals. And so what we did is we started defining periodicity on the reals in order to then generalize it to timescales. All right? And the way we went about it, you may have seen this already, right? I said the areas are equivalent, but you can really write this as nu delta f nu equals f. This is where it reappears, right? Now you have nu prime f nu equals f. All right, and so we define periodicity in that 2024 paper. We define periodicity with respect to a strictly increasing function nu. All right, and right, and we denote those by p nu I. Yeah. All right. Yeah, so if we define it for the reals, I mean, we do all kinds of things, so if this interests you, yeah, if you can't find the paper, let me know, I'm happy to share it. But we can now define those Cushing-Hansen conjectures or investigate them for the continuous logistic model, okay, that is not known for this new type of periodicity. And I'll show you why that would even matter, okay? So this very classically the logistic model. And now we have R and K could be time-dependent functions. And so what we say is, in order to define the Cushing-Hansen conjectures on the logistic growth model, we are not requiring R and K to be omega periodic, but rather this adjustment, okay? So notice, I should say this. If you choose, okay, no space. If you choose your new T to be T plus omega, you're gonna retrieve exactly the classical definition of periodicity, right? Because nu prime is just gonna be 1, it's strictly increasing. You're just gonna get 1, correct? And so you're gonna have F, so nu prime is 1 times F nu, that's just gonna be F evaluated at T plus omega equals to F. That's exactly your classical definition. But we don't restrict it to T plus omega. Could be any type of function, all right?
Strictly increasing.
Strictly increasing, yes, that's right. And so, but what you notice is if you were to choose this classical definition, nu prime is 1, nu double prime is 0, this is gone, and you're going to get R nu, which is RT plus omega equals RT. That's your classical definition of periodicity. But if we look at it for a more general function that is strictly increasing, we'll get this particular condition as an equivalence of our classical R being periodic case. And then instead of K being periodic, we have to basically adjust that definition. We have R over K to the nu being R over K. All right, so if we make these two assumptions, we can now guarantee that, assuming ER is greater than 1, that we're going to get a unique omega periodic solution. We can write down an explicit form of it, right? That's maybe not that surprising because it's a logistic growth model. We can always solve it, right? But it's a unique omega periodic solution, and we can show that it is globally asymptotically stable for positive initial conditions if we make the assumption that our K is bounded, yeah? All right. So this would be our first, this in the reals, yeah. Right, it's the logistic growth model, and this is the first Cushing-Hansen conjecture, okay? Unique omega periodic solution, that's a global attractor. Now you may ask, why would we care? Okay, so hopefully I can convince you a little bit. So if we were to take, okay, so Beverton and, okay, Cushing and Hansen, in order to come up with those conjectures in the first place, they used particular flower beetle data, as I said, right? So they did it for the Beverton-Holt model, but of course we can also fit that to a growth model, to a logistic growth model, continuous model. And so you see here the dots are your data points, and we make a fit of a least square minimizer, and we're gonna get that one in the middle. Okay, this is our best fit, and you see that we have a starting value. This is the starting value of our unique omega periodic solution. So it defines completely my omega periodic solution, right, because it's unique. And I have an R bar and a K bar. Okay. Now this is the best fit, but we can also describe this best fit as the new periodic solution to this particular nu function that we see up here. So we can express this solution with respect to a function nu, so that the best fit is a new periodic solution. All right? And then of course, if we were to change that nu, we would get other forms. These are not the best fit, right? They're just some other solutions. But we can find values for this particular nu so that we can express our best fit solution as a new periodic solution. Now you may still ask, why would we care? Okay, so what we know is that under certain conditions, this new periodic solution is a global attractor. So we have a time-dependent function that is a global attractor for a non-autonomous differential equation, right? And so what we do is, we can see here we have non-autonomous differential equation. We have R over T and K not over T, so that's non-autonomous. But we can, since we have our new periodic solution, that's the red one, we know it's a global attractor. So if you start anywhere else, you converge to this time-dependent solution. Okay? So again, even though it's non-autonomous, we really don't have to rely on the non-autonomous theory that much, because actually not, because all we do is we identify the solution that is new periodic, it's a global attractor, and we can say how all the other solutions behave in a limit. All right, and so what we see is that these other solutions starting somewhere else, they all converge to this new periodic solution. Here it's just showing that we basically get the same, the integral is constant, right? We always go to 1, the C is normalized, right? I told you that new periodic solutions or functions, they have an integral that keeps repeating, and so that's what we see here. Or probably a bit more vivid is that we notice that these areas are repeating. So even though they look very different, the area underneath that function with the different shades is actually the same value. All right. Now to the second Cushing-Hansen conjecture, we were able to make an analog so that if we assume, and it's a little cumbersome because you need to have the existence of an H, so we had to use some functional equation theory to show that such an H can exist, so that the EH is equal to 1, you need that H, and then define a corresponding phi, right, that is R minus H, and you essentially can show the second Cushing-Hansen conjectures again as a weighted average. Okay, so it's only equality if your R over K turns out to be constant. But what's so cool is, in this example, right, R and K are time dependent, but R over K is just constant. That's just R naught over K naught. So even though it may be time dependent, you may still satisfy that R over K is constant, which means that you get equality here, and you know exactly how your average of the periodic solution behaves. And you can then compare this, of course, to the average of the carrying capacities. And so what you see here is, maybe let's focus on the orange dotted and the purple dotted. The orange dotted is your average of the solution, of the omega periodic solution. And we are in the case where R over K is constant. So we can, without knowing the solution, we can just take a look at this weighted average on the right-hand side. We know it's exactly the same. And we see that it is always above the average of the carrying capacities. That means what? It's actually beneficial in this case to introduce this type of periodicity so that we have our R over T and K over T, even though it's not that obvious. But of course, it's not always beneficial, right? So if you change your parameter values, then you could have the case that there may be some time where it's actually deleterious before it becomes beneficial. So one way would be to study this and make that more applicable to different species, but that's something we didn't do. All right. But of course, I'm going to use the last 5 minutes to, okay, one more time. I know it's been quite some time now. Okay, starting out with discrete, we went to isolated timescales for periodicity, then to the continuous case, so we can discuss non-autonomous differential equations. And now, of course, the holy grail is to do this on timescales, yeah? But now what we have is, we basically have the toolbox from our continuous formulation, where we use nu prime f nu equals f. Now we know exactly, okay, in the timescales we may want to discuss nu delta f nu equals f. And that's exactly what we then did in another paper that was published last year, where we assume nu to be again strictly increasing, and we want to make sure that we map the time domain into the time domain, so nu t is t. All right, and so yeah, here are some lemmas. Basically, we are closed under we are closed under addition and scalar multiplication, and we see the invariance if we integrate over one period. it doesn't matter where we start, so very classically that invariance of our areas, and also as long as we integrate T to S and we apply our transformation that is nu, right, the sigma omega T, then that's exactly the same. And if our F is nu periodic, then we know that our EF, that's the timescale's exponential function, is just going to be T independent, okay? So, and we can use these properties, and there are many more in the paper if you're interested in.
But the last one also, the mu cancel.
Yeah.
And you can always think about T plus omega is one, and the other one S plus omega, right? And then if you subtract these two, the omega cancel. So these are really great generalizations of that thing.
Yeah, and then, yeah, exactly, and yeah, this is very critical for our solutions where we. So in this particular paper, right? So we didn't solve the Holy Grail yet. So I guess I still have to. The Cushing-Henson still is with me for a little while at least. So right, but. We can now address the existence of omega periodic solutions to linear equations, linear dynamic equations. And we want this because remember the Beverton-Holt model reduces to a linear model once we make that transformation, right? 1 over y. And so you notice that it's not trivial, I think, like you cannot look at it and say, oh yeah, that was clear that this condition has to be satisfied to guarantee omega periodic solution. Yeah? So, but yeah, I mean, this was really the key, I think, came from the real case, where we noticed that this was nu double prime plus nu prime. So not immediately, but there's at least some relation to it. But yeah, so the bottom line is, if your A is omega periodic, you are not guaranteed to have an omega periodic solution. You actually need to satisfy this strangely looking equation in order to guarantee the existence of an omega periodic solution. And anything that I say, right, can also be applied for this Y sigma. So in the same way that our Cushing-Henson conjectures could have been equally formulated for the type of logistic model that Maria de Lemos Silva studied. Right, anyway. Okay, so we have here some result about the existence of a solution in the non-homogeneous case. And again, this is the building block for us to study this for the Cushing-Henson conjectures for the Beverton-Holt model. So yeah, Martin, that comes to our to-do list, or my to-do list. And yeah, maybe since I'm a little late, so thanks and happy birthday, Martin.
Any questions or comments to Sabrina? We have some time.
Was the second Cushing conjecture on timescales in your presentation?
Yeah, so about to come, yeah. So, yeah, thanks. So in order to complete the study, the last step is exactly just to formulate first and second on the general timescale, using that completely new definition of periodicity that we published in 2025. So 2026 should be the year. Every year another paper. But yeah, we have all the building blocks, so I'm confident we will finally finish. But we did formulate it for the isolated timescale. We formulated it for the continuous case. And now that we are in the timescale, any general timescale, and we have that periodicity definition, we are confident, optimistic that we can finish. Yeah.
Okay, I mean, here is interested business Beverton-Holt, right? But here you have a definition of periodicity that you can, this is at your disposal. You can do anything you want with this.
Yeah.
Everybody here who was interested in periodicity in any, I mean, even in the real case, you, right? So for anybody, you're welcome to use that. Maybe cite the paper. and getting your results.
Yeah, all we did is for scalar, linear, right? We were only able to so far publish what are the conditions to guarantee the existence of an omega periodic solution for the linear scalar case. But yeah, you can cook up any higher dimension problems, right? And yeah, anything you can think of that requires periodicity. So you don't have to require the time domain to be periodic. Yeah.
Any other questions or comments?
Can you go to your lambda thing on the next slide?
Yeah.
Right now, is that lambda something that will make advanced things something wrong, or?
Yeah, so I think that did I not copy this probably? So the lambda is coming from your solution, right? It's capital EA, and that capital EA, yeah, here it's defined. So that is A delta EA nu TT. So it's given by your coefficients of that, yeah, of your problem. So you don't pick it. It's determined. Yeah.
Actually, there is an extra part. I mean, this is when EA of T0 is not 1.
That's right.
But there's also something when it's equal 1. You didn't show us this?
Yeah, I kind of just jumped over it.
Okay,
Yeah, you're right.
And then there are 2 more cases in one. I mean, in that first case, it was unique, right?
Yes.
That here, whatever it says.
But here it says that if EAT is equal to 1, if this integral is equal to 0, then all solutions are new periodic, and otherwise there is no non-trivial new periodic solution. Right? Because the 0 solution is always the trivial one. Yeah.
Okay, any other questions or comments? If not,
Just
okay,
one
sorry.
more thing. I mean, even if you're not interested in timescales, please use our definition: nu prime of t, f of u of t equal f of t. Yeah? The only difference, forget the timescales.
Yeah. This is this one, exactly. And I think there is potential, yeah. We used it to study non-autonomous differential equations, but there are many other ways, yeah.
Okay, so what journal is it published in?
The continuous one,
This definition, is it published?
is that the one in chaos, solitons, and fractals?
So your new definition
Yeah,
of your
the new definition for periodicity we published in chaos, solitons, and fractals, right? Huh? Well, okay, hold on. This is the name, and I promise you we don't publish the same paper with the same name twice. So if you type in that name in Google Scholar, you will find us. But I'm very happy to share.
But I think it's right. It's all solitons.
Yeah.
It's in that journal. Chaos, solitons, and fractals. Any other questions or comments? Okay, if not, so let's thank Sabrina.
On the time scale, REL. Yeah, isolate, but not beyond. It's at the bottom of Brasilia.
No.
Okay, so let us continue, and it's my great pleasure to introduce our next speaker, Professor Agnieszka Malinowska, and I'm very glad to have you here. And today she will talk about fuzzy quantum symmetric variational problems via granular approach. And before I give the words to her, I will give to Martin because he's already prepared to say some words.
Oh, I just learned that she is speaking. I don't have the schedule. I guess Agnieszka, we know each other also since 2010. We met in a bar in Aveiro, right? When she showed me this bar, I was so happy. It had a German wheat beer, my favorite one. And then it was, then we drank one, I guess, and I wanted another one. But she broke the bottle. And that was the last one they had.
Okay, thank you very much for introduction, and also I thank you organizers, Jacqueline, Tom, and Sabrina, because it was a really great idea to organize this meeting, and I think everybody is very happy. I also am very happy to be here. Okay, then to this strange title maybe, because I have known so many papers with Martin, in fact. I count, it is 5 papers, and 3 of them, they are connected with one guy, in fact from Vietnam. So firstly I will say the story, how it was happened. So once upon a time, it was after the COVID time, people started to travel, not Martin. But I attended the conference in Porto, and I was in person, Martin was online. And go to the authors, it will be easier. And this guy is Truong, came to Porto, and the reason was he wanted to speak with Martin and with me. Okay, Martin wasn't there, so okay, he had to speak with me. Okay, and then he proposed what we will be, what we can do together. Yes, it was about this granular approach. Okay. Moreover, the other thing is that this guy Tri was a student, PhD student in Austria, and his supervisor was Baruch Schneider. Okay, and so then Tri visited me, I think, 3 times. So, and also once, I think he was in Rolla. I think once, in my case, yes, it was 3 times. And we wrote in such a group that it means Tri, me, Eva Girejko, she is my friend from my university, and Martin, 3 papers. And one of the paper is this one. So what more? This paper was published last year, and it is a computational and applied mathematics. In fact, it's also connected with Brazil, because this journal is a guy from the Brazilian Society of Applied Mathematics. This is the thing. More thing, it's also about Susanna, because she was in the jury of 3 out of the PhD, yes. And after that, 3, I think, stay 1 year with Rome. So it's many people are connected, and it was the reason that I choose this subject. However, I am not an expert in fact, let's say, about fuzzy functions and fuzzy numbers. I don't know about Martin, but I suppose he is good in all topics in this. Okay, so what is the aim? What was the aim of this paper? That we joined together 3 concepts. It means Q-symmetric quantum calculus, fuzzy functions, and granular differentiability. This granular approach is rather new in fuzzy numbers, in fuzzy calculus. And what is also interesting, this approach was invited by 2 Polish people, Biega and Landowski. They are working in Szczecin. Okay, and so what we did? We defined the Q-symmetric calculus for fuzzy functions, and this is based on the granular difference and the concept of the horizontal membership function. And then we propose a novel concept of differentiability and integrability for fuzzy functions. And finally, I will show the result about the optimality conditions for a fuzzy Q-symmetric variational problem. Okay? About the Q-symmetric derivative. We used, in fact, the paper of Cruz and Martins, and they work with this Q-symmetric derivative. So how it is defined? We have a Q between 0 and 1, and we define such a set I subscript Q in the following way. We assume that 0 belongs to this interval. Okay. Then for a real-valued function, we define q-symmetric derivative in the following way. So you see that it's a little bit general that we went with q calculus. Okay, in the case when we have 0, we just use the usual derivative, provided that this function is differentiable at 0. Then how it looks, the q-symmetric integral. Is defined in this way. So if you have integral from a to b, you divide by 2 from 0 to b and from 0 to a, and this integral is defined as this series, provided of course that this series is convergent at t equal a and at t equal b. What more we will need further is that we define such a set set within the subscript q, and I would say that is the set from A, B, let's say Q set. Okay, it will be easier A, B, Q set. Okay, and here you have an example how it works. So here we consider the set from -5 to 5. And we have the function which is exponent minus 2 power 3, and with q equals 0.9 we have the following graph. So as you see that we have convergent to the 0. Okay, now we will go in the direction of fuzzy numbers. First I need to introduce the relative distance measure. So if you have a set A, this value is set the relative distance measure because this value informs us about relative position of any value of A inside the set A. Okay, now fuzzy numbers. So what is a fuzzy number? Fuzzy number is just a fuzzy set. Fuzzy set, it means that all elements of the set has the degree of membership. Okay? And this fuzzy set should be normal, convex, upper, semi-continuous, and compactly supported. We will denote this set of fuzzy numbers by R with some okay? And in the case of 0, we have the situation that the degree of membership at 0 is just equal to 1. Okay, the next thing which we need is the alpha level set for the fuzzy number. And this alpha level set is given by this expression for alpha which is greater than 0. And in the case when we have 0, we need to take the closed rows. Okay? And what is what we can say, this is about how we can represent this alpha level set. And here is the notion. In this notion, we use the lower branch of fuzzy number and the upper branch of the fuzzy number. So once again, this is important for us that the alpha level set can be expressed in the following way. And in fact, usually when you have arithmetics with the fuzzy numbers, usually you use this lower branch and upper branch in the arithmetic. But what was introduced by Curators and Landowski is a little bit different. Because in this case, they define the horizontal membership function. And in this horizontal membership function, you have two variables. Not only alpha, which is this level, but also this relative distance variable, yes? Which is here. So you will have here information not only of the lower branch and upper branch, but also about all variables which are inside this fuzzy number. Okay, and this transformation
And the mu is between 0 and 1, right?
Yes, yes, yes,
Ah, yeah.
because it is was relative distance measure,
Yeah.
what is in before. So it's and alpha also, yes, between 0 and 2. Okay, then, so further I will say that this is a gradual, representation of the fuzzy number. So here we have this gradual representation of the fuzzy number, but from this representation we can go to the alpha level set. So if you want to go to the alpha level set, we need to use this formula 3. Okay? So you have this gradual representation, and here you just need to find minimum and infimum with respect to alpha and with respect to this relative distance measure. Okay, how we do operations arithmetic on these fuzzy numbers with this gradual representation? Of course, using this gradual representation. And this, once again, is a little bit different when usually use fuzzy numbers. Once again, because usually they use this lower and upper branch. So what we do? First, having a fuzzy number with fuzzy numbers, we use this gradular representation. We do operation on this gradular representation, and by this formula 3, we are going back okay, to the alpha level set. And for us, it will be important this granular difference. Okay. Now, a little more complicated thing happened because when we have just one fuzzy number, we have for this fuzzy number one relative distance measure there, yes? But if we have more fuzzy numbers, then for each fuzzy number, we will have this relative distance measure. So in the end, when we do operations on fuzzy numbers, yes, arithmetics, by adding two fuzzy numbers, we will have the dependence of two relative distance measures. But anyway, as you see here, it is possible to work with this. Just if we want to have alpha level set, we need to take minimum, taking into account more relative distance measures, which appeared previously in those fuzzy numbers. Here maybe example, it will be easier to understand how it's going on. So we have two numbers, trapezoid fuzzy numbers, and for them we can create alpha level sets. So it's for U tilde and V tilde. Then from this alpha level set, we are going to this granular representation. Okay, you have alpha and you have this relative distance measure for the first function, for the first number, and the same situation we have for the second fuzzy number, and here we have different relative distance measure. Yeah? Maybe also graph. It's always useful to see how it looks. So the first number, this is for fuzzy number U tilde. So you have a situation. This red is our fuzzy number. Yes, trapezoid fuzzy number. You have the lower branch and the upper branch. Okay. And then what is important, when you have the relative distance measure equal 0, you have this part. Yeah. When you have relative distance measure, it means that you is here, so is upper branch. Okay. But also you can have more information thanks to this relative distance measure, because here you have illustration. It's the case when mu is equal 0.6, then you have this line, and for alpha equal 0.5, you will receive the point which is in the interior. But once again, when you are working normally with fuzzy numbers with arithmetic, the you only work with lower and upper branch. Okay, and here is also the graph, how it looks, the horizontal membership function. In this case, it's the function of two variables. So you have alpha here, and then is this relative distance measure, and here you have this regular representation of our number. Okay. Now, so let's recall how we are doing arithmetic operations. So we will say that this, as I previously said, that what we are doing, we have this granular representation, we just do arithmetic. So you see that in the result, you have two variables, this relative distance measure, which you have first alpha, and then you have mu, okay, which is connected with this number u, and also additionally mu v, which is connected with this v tilde. And the same situation when you have this granular difference. Once again, first we are doing this granular representation, and we are doing operation. Okay, so here we have the result. So it means that when we have this granular representation, you are going back, and you can write how it looks this alpha level set. No, and as a result, we obtain this trapezoid fuzzy number. And some graphs. Also here we can see how it looks our fuzzy number u and v, and what is the operation of adding those two functions. And here we have representation of the horizontal membership function for all those fuzzy numbers. And this is when we subtract those two fuzzy numbers. Here is the degree of membership, and here we have this different representation. It is with this horizontal membership function. Okay, now more about these fuzzy numbers. Okay, we say that two fuzzy numbers are equal if and only if we have the equality with their granular representation, and it should hold for all mu and mu and mu v. So for two relative distance measure which are connected with those two fuzzy numbers. Okay, and then we will have also the partial order is given. This is a partial order because it is not always like that we can compare two fuzzy numbers. And the same situation is here. That we have that this fuzzy number u is less or equal to v, if and only if the following equality holds for this granular representation, but it should hold for all relative distance measures connected with those numbers. So as we want to work with optimization, we need to assume that all fuzzy numbers will be comparable. What more we need? Here is granular distance between two fuzzy numbers, and it's defined in the following way. So once again, we are using this granular representation. So first we do granular representation of the u tilde, v tilde, and then we are taking just maximum and supremum. It was proved by Biegat and Landowski that this space is a complete metric space. Okay, now something about fuzzy functions. So we will consider fuzzy functions which are defined on the real interval. And as it was with arithmetic operation on the fuzzy numbers, the same situation will be with the fuzzy functions. Because those fuzzy functions will depend also on, let's say, n fuzzy numbers. So with each fuzzy number, we will connect its relative distance measured variable. So in order to show the notation, we'll just do this mu with some f, capital F, because of the fuzzy function. Okay? Okay, so now how we define the granular Q-symmetric derivative of the fuzzy function. So what we are doing, the definition is here. So as it was for the real function, definition it looks in the same way. Let's say just we have those fuzzy functions, and here we have granular difference. Of course, in the case when we have zero, as it was for the Q-symmetric derivative, zero, we had the usual derivative. So here is the same situation. So and in the case of zero, we assume that f is granular differentiable at zero. And this definition already exists. Okay? There are papers by Biegan and Landowski, it was already introduced. Okay. So okay, it works, it's theorem. So if f, fuzzy function f, is granular Q-symmetric differentiable, if and only if its granular representation is Q-symmetric differentiable with respect to t. So what it means that if we want to find this derivative, we need to go to its horizontal representation and take the partial derivative, partial Q-symmetric derivative with respect to t. This operation is like that. Once again, we have fuzzy function. We are going to granular representation. If we have the granular representation, we can just use the definition of the Q-symmetric derivative. And here is the example. So we consider a fuzzy function on the interval from -2, and this fuzzy function for each t, yes, it's a triangular fuzzy number. Then we, in order to have this granular representation, what we have to do? First, we need to write the alpha level set, and the alpha level set is written here. Yes, this is the alpha level set. So, having this alpha level set, we introduce this relative letter additionally. This is here. And so here we have already this granular representation. Very important. And if I want to have the Q-symmetric derivative, I just take the Q-symmetric derivative, taking into account this granular representation. Yes. Here is just the membership function for our fuzzy function. This green is for alpha equal 1, and here you have the horizontal membership function for this our fuzzy function. And the calculation, as you see, so if I want to have this derivative, I am going to this granular representation, I am taking the Q-symmetric derivative, I have the following expression. Having this, I can go to alpha level set on the derivative, and I obtain the following alpha level set for this derivative. And here we have the graph. Here this with the horizontal membership function when we have, when we have this relative distance measure equal 0, we have this value which is up, and for mu equal for mu f equal 1, we have the lower frequency. About the integral. So once again, the idea of the integral is like that. That first, having the fuzzy function, we are going to use granular representation. Having this granular representation, we can just use the definition of the q-symmetric integral. Show that this what is written. Okay, the following theorem also it works nicely. Derivative and integral, and maybe I will show this example how it works. Okay, this was our example, yes, with fuzzy function, and we calculated the fuzzy q-symmetric derivative. Then you have the granular representation. Okay, so having this, we can we just put this horizontal representation. We have this, and having this expression, we are going to the integral. Yes. So this is this granular representation. We put the integral, this q-symmetric integral, and we can calculate using the rules which are for the q-symmetric calculus. So in the end, the result is here, and vice versa. We can do the operation. So we have this function f, and we can do operation, just arithmetic operation. Then so we calculate the value of our function at 2 minus the value of the fuzzy function at 0, and as you see, both sides are the same. Variations and the fuzzy q-symmetric variational problem. So the problem, as we see, is 7a. It's a little bit general variational problem because we can also consider these boundary conditions that would be in the Lagrange. Okay, but I will show only one theorem where there are necessary optimality conditions where we have fixed boundary conditions. Okay, so everywhere we have fuzzy numbers and fuzzy functions. Okay, so definition which we also need, it means the space in which we are looking for a solution. So this capital B0. Here we consider such fuzzy functions which granular representation is bounded on our APQ interval, and they are continuous and 0. And the other set, it's V1, and here we assume that also when we count the fuzzy q-symmetric derivative, and then when we take this granular representation, it will be bounded on the APQ set and continues at 0. Okay, we know our space with the orbit. And some definitions which are usual for a variational problem. It means what it is the admissible admissible fuzzy function for our problem. So as usual, that it should satisfy these boundary conditions, and what we say about the admissible fuzzy variation. As in the usual case, we define that it should be 0 at the boundary point. Okay, and then here we have once again this partial infect order, because this was assumption that we are working in such case that all fuzzy numbers are comparable. what is the idea? Of course, as it was with arithmetic, as it was with the Q-symmetric derivative, first we should go to the granular representation. So we are going to the granular representation of the variational problem. And it looks as follows. So we have our functional here, and here we have boundary conditions. Everywhere we have this granular representation. Okay, some things which I have to recall from the paper of Bruch and Martins. It means how we calculate the first variation of this functional and assumptions under which this first variation exists. But I will not concentrate so much on this, just this proposal was proved in the paper of Bruch and Martins. So it is, those assumptions are connected with this Q-symmetric variational problem. So I had to put all those assumptions because, as you suppose, when I had this fuzzy variational problem, I went to this granular representation. When the granular representation is already the Q-symmetric variational problem. Okay, one more assumptions. There are really technical assumptions in order to obtain the Lagrange equation, and all of them are connected with this granular representation of the Lagrangian, which is our function. Just short notation. What I want to say, it's this theorem, one of the theorem which we proved. So under assumption that granular Lagrangian satisfies all our assumptions, it means from A1 to A4 and all the assumptions from the proposition. If x tilde star is a local minimizer for our variational problem, then it should satisfy the granular Q-symmetric Euler-Lagrange equation. So in this Euler-Lagrange equation, you can see that it's very similar in other cases, in other calculus. Just everywhere we have this granular representation. An example. This is our variational problem. And we have boundary conditions which are granular fuzzy numbers. Of course, based on the theorem, if x tilde is a local minimizer for our problem, it should satisfy this granular Q-symmetric Euler-Lagrange equation. And this equation is easy to solve with our boundary conditions, and we get this granular representation of our minimizer. Okay, from this granular representation, we can go to the alpha level set for solution. And moreover, we see that our problem is convex, so in fact we have our minimizer. And here you can see the graph with q equals 0.9. This is the membership function here. So when we have this free, it is for alpha equal 1. And the horizontal and the granular representation of our minimizer. So this upper is for relative distance measure equal 1 and lower for the relative distance measure equal 0. Okay, in the paper we have much more results, but I decided to just present one. I know that it's completely different subject of people speak here, but once again, it was the reason about those three papers. So here you have some references regarding fuzzy numbers and this new arithmetic of for the fuzzy numbers. It was introduced by Tigran. The paper, the q-symmetric variational calculus, which I already mentioned during my talk, yes, that we use this paper. Okay, the paper on which I based my presentation. And there are two other papers which we, let's say, produced together. So they are already published, but in fact, the story finished. We don't know. We will not for sure continue this. Okay, thank you very much.
Any questions or comments?
Thank you for your interesting talk. I have some questions. You don't have a total order. You have just a partial order.
Yes, yes.
How do you establish, order of equation?
That's why I said that is the thing which we had to assume, that this order exists. Yes.
Exists, but you didn't use because the granular order is not a total.
Yes, I agree. This is not total order. That is the problem for optimization. That is the assumption which we put. Yes, and mostly in when you work optimization fuzzy functions, yes, and optimization is the thing that you have to assume something. Yes. At least what I learned, because it's not really, once again, this is not really my subject. Yes. But while working on this paper, we have to analyze different approaches to the arithmetic of the fuzzy functions. Yes. So as I said, usually in those approaches they work only in the bounds. Yes, of fuzzy numbers, not with the integral. So this approach is a little different, but also good because you have a unique, let's say, sometimes solution. Yes, if you work with this lower and outer bounds of the fuzzy function, you will have two solutions. Yes, so it's not a unique. For example, this is.
Yeah, but otherwise, how can you associate order Lagrange equations with your solution? Because you need, the optimal condition.
That's what I showed. This optimal condition is the Euler-Lagrange equation. But what we are doing is this simple rule. Yes, you have this, let's say, fuzzy variational problem, okay, and you are going to this granular representation, and then in this case you are not working anymore with fuzzy problem.
I know, you go to the function class.
Yes,
yeah.
then you use this calculus. In this case it was q-symmetric calculus, yes. But you can also use normal calculus, let's say.
Okay. Just one more question. In the Lagrangian, you have the derivative of the second argument or the third argument, and the Lagrangian involve the arguments are fuzzy numbers. And the derivative is respect to a fuzzy number. How you handle this problem here?
If I am already with this granular representation, I look and I just put some assumptions, and I am using the rule which is already done for this q-symmetric variational problem. It is like that.
Yeah, you having a function. You having a functional representation. I know.
Yes.
I know. But the problem is your derivative respect a function. It should be, for example, Fauché derivative, something like that. It's not about the alpha or other things. Do you get my point?
Yes.
Yeah. You have a problem
okay,
with that.
I understand what is the case. This is you speak about the first variation.
Yeah.
Yes, but once again, if I am in this Q calculus, this is not. Okay, so I had a problem with fuzzy variational problem. Right? The idea was to go to the q-symmetric variational problem, and now I am in this problem already. Now, if I am in this problem, I use the tools which are known for the q-symmetric variational problem. And this is what I said about this proposition, which was proved in the paper of Kuhn and Martin. And this is about what we are saying about the first variation. Yes, exactly. And this is here, and I am assuming this, that is possible under those assumptions. I can calculate the first variation you have here. Yes? This is the thing.
Okay.
This is the operation. And in fact, this is one approach, but if you see the different approach to the fuzzy function with those bounds, they are doing very similarly. Yeah? They are taking just the left and the right bound, and they are doing the same operation.
Yeah, right now you have different approaches to fuzzy calculus.
Yes.
It's granular just once.
Yes, that's just a different.
Okay, I have a lot of questions, but I can talk later about that. Okay.
Okay.
Thank you.
No, I'm very happy that there is at least one person who is interested in this. Because when I'm looking on the audience, I was, they will start to sleep immediately. Immediately they will be sleeping. So yeah, but okay, one second. Okay. The explanation you already hear. That's why I speak about that. Okay, I'm very happy for the question.
Yeah, there is actually a big group here working in fuzzy, so yeah, so it would be very nice that you can also talk later. Martin, you have a question?
Why did we use this Q and not this like arbitrary isolated? Because of that Martin's and Cruz paper, or
because it was like that. He was not there in Porto, and it's simple. Because he came to me and he asked if he can work on this specific paper. I said, okay. I was not thinking so much. Okay, let's go with this view. But I think it would be possible to do completely different approach on isolated time space. I agree. I agree. But you know, you didn't want to travel. No, the fault is yours. Not us.
More questions or comments? Just very quick, you mentioned that it's possible to do for isolated timescales, and in general, for general timescales, or no?
I think if we use this approach, I think yes. You know, maybe on the way can be some difficulties, but I think probably yes. Probably yes.
Okay.
But I left this, so I cannot say. Now the tree is in Vietnam, so it's those.
Okay, so without knowing, you choose a very good topic. As I mentioned, like we have a strong group here working fuzzy, so yeah, more one connection than the others that you brought. Yeah, so let's thank Agnieszka again.
And okay, may I say something? Okay, but it will be not connected with Martin. sorry about that. Because I want to do a little, like saying in Portuguese, propaganda. Because I'm organizing a conference in my city, Białystok, and so I have some advice. If you are interested, I will give you those. Maybe you will be, you can share with your colleagues at your university. Maybe somebody will be interested to come. In fact, this will be also workshop today, which is completely free. It will be about optimization in machine learning, but tools using this mathematical approach, yes. And also about fractional calculus and applications to optimization on or any other applications. I think I gather nice people who work in Poland and in Germany. Some of them I choose, the other not, so sorry that I didn't invite you. But in September, you don't want to travel once. But you are very, very welcome always. Yes, if you can come, I will be very happy, as usual. Okay, so a little propaganda. Thank you.
Okay, very great. So thank you very much, Agnieszka.
I show you this when I'm having exam. So please, one student.
Okay.
Yeah, I did the exam paper. I don't know if QR code is working because something happened.
Okay, so let's continue with our next speaker, and it's my great pleasure to introduce our next speaker, Professor Marielle Aparecida Silva, my academic sister, and today she will talk about on-oscillation theories for generalized ODEs. So thank you very much, Marielle.
Thank you, Jaqueline. So, good afternoon, everyone. First of all, I would like to apologize for my English. It's not very good. It's been a while since I gave a lecture in English, so apologize for that. Well, my name is Marielle. I was a student of Marcia Federson in São Carlos and Everaldo Bonotto, but now I am a professor at the Federal Technological University of Paraná, and today I will talk about my work in oscillation theories, in particular oscillation theories for generalized ODEs, all right? So, before I begin, I would like to congratulate Professor Bohner on his 60th birthday and also for all his powerful contributions to mathematical research. Congratulations, Bohner. And also, I would like to thank the scientific committee of this event, in particular Professor Jaqueline Mesquita for the invitation. It is a great pleasure to be part of this celebration. So, thank you. So when we think about oscillator functions, we generally think about the following definition. A function, f, is oscillator function if for every t in R that exists s greater than t, such that this condition here, this inequality here, is satisfied, all right? So in this case, we have this behavior here, all right? So, but we could also think about oscillation for functions taking values in Rn, all right? In this case, we propose the following definition. A function f is said to be oscillatory if at least one of its component functions is oscillator. So we decided to work with this definition, analyze some simple cases and applications. For example, consider this function here. We know that the sine function is oscillatory function, right? So in this function here, the second component is oscillatory function. Then we have the curve of the function f here. So there are applications in physics. A Lissajous curve is the graph given by a system of parametric equations in the form here. We know that x and y are oscillatory functions. So now we present some examples of Lissajous curves. And know that these curves exhibit oscillatory behavior, all right? So in this paper here, we presented results about oscillatory solutions of generalized ODEs and other types of differential equations using the definition of oscillation in Rn. But I will not talk about these results today because our interest lies in the more general case, where the functions take values in any Banach space. So, if X is any Banach space, we cannot use the oscillations definitions present previously, because in some of this space, we have no notion of order, all right? So in this paper here, we begin to get an idea of how to define oscillations for functions taking values in Bohner space. Table presents the idea of composition with functional, all right? This idea is the following. Just a minute. Consider F, take values in a Bohner space, all right? So F is strongly oscillates if for every functional zeta, for every linear functional, the composition here oscillates in the classical sense, all right? That is, there exists S greater than T such that this inequality here is satisfied, all right? So we have the following definition. Let X be a Bohner space. By X star, we denote the space of linear functional on X. So a function F strongly oscillates if for every linear functional zeta in X star, the composition here oscillates in the classical sense. That is, for every t greater than or equal to t0, there exists S greater than t such that this inequality here is satisfied, all right? So now with this definition of oscillation in Bohner space, we can prove oscillation results for the case where the functions involved in the differential equations take values in any Bohner space. So now I will go talk about the goals of this lecture. The initial goal of the result was to construct an oscillatory theory for generalized ODE taking values in Bohner space. So along the way, we proved an oscillation theory for evolution process. And as a particular case, we obtained this theory for generalized ODEs. So we introduced the theory of pullback oscillation for linear evolution process. Necessary and sufficient conditions are presented to obtain pullback oscillation. We investigate the oscillatory behavior of solutions to linear generalized ODE, where the functions involved in the differential equation take values in a Bohner space. And finally, using the theory of generalized ODEs, we apply the main results to a class of ordinary differential equations. So all the results I will present here can be found in this paper, which is a collaboration with Professor Marcia Federson and Professor Everaldo Bonotto, all right? So now I will talk about oscillation theory of linear evolution process. Let X be a Bohner space, and we denote by L applied to X the space of bounded linear operators. A linear evolution process on X is a family of maps S applied to T and S so that T greater than or equal to S satisfy the following properties. First, S applied to T and T is equal to the identity operator, and this equality here is satisfied. It's important to note that we don't not assume continuity for the mapping S. For example, let U be a regulated function and F be a function so that F is a Perron-Stieltjes integrable function. So it's possible to prove that this family here is a linear evolution process. And the continuity of the map of this map here depends on the continuity of the function U. All right. So In order to present the concept of oscillation using pullback dynamics, we call the definition of a pullback arc. So, the pullback arc of a subset B at time t with respect to a linear evolution process S is given by the following set here. And a cone C is a set that satisfies the following properties. First, if U and V belongs to C, then U plus V belongs to C. If U is in C, then this element here is in C. And we need the following definition. Given a subset C, the following set is called the closed conic hull of C, all right? So, now, we can present the definition of pullback oscillation. So, a point X in X, pullback oscillates at time t0 with respect to a linear evolution process S if for every linear functional zeta in X star, the condition is satisfied. For every R, n can find S1 and S2 so that this inequality here is satisfied. Note that S is a linear evolution process, all right? So we use here the composition of linear functional because X take values in abundant space, all right? So we worked with pullback oscillation because we used the theories about pullback dynamics, all right? So now we can prove the following result. The theorem 1 provides conditions for a point in any bounded space to be oscillator. So consider T0 in R and assume that X belongs to the set and S is a linear evolution process. So if this condition here is satisfied, then it's possible to prove that the point X pullback oscillates at time t0, all right? So the proof of this theorem is complicated. Then I will not present it here, but for the proof of this result, we need the following results. First, let's see in X and consider Y in set. Then there exists a linear functional zeta in X star such that this condition here are satisfied. And let X and Y be bounded space and T be a bounded linear operator. If S in X, then this condition here is satisfied. So now, I will present an example. Consider the following linear process, evolution process. So from theorem 1, it's possible to prove that every point X pullback oscillates at time t0, all right? So it's possible to prove that this result. Consider the number t0 here, X belongs to the set, and S, a linear evolution process. If X pullback oscillates at time t0, then this condition here is satisfied. So, for the proof, we assume that X pullback oscillates at time t0, and this condition here is satisfied. So, by lem A, there exists a linear functional zeta in X star, such that this condition here is satisfied and this condition here is satisfied. But it's possible to prove that this contradicts the fact that the X pullback oscillates at time t0, right? So now, I will talk about the important result. This next result provides conditions for a function f taking values in abundant space to be oscillatory, all right? So let f be a function. If there exists a number, t0, greater than 0, and a sequence such that this condition here is satisfied, and f applied to minus t0 is equal to 0, and this condition here is satisfied, then it's possible to prove that the function f strongly oscillates, right? So for the proof, suppose that f doesn't strongly oscillate, then we assume that there exists a linear functional zeta and t such that this inequality here is satisfied for all t greater than or equal to t. So define the evolution process by, that is, s applied to t and s applied to x is equal to this function here, we obtain a contradiction. So it's possible to prove that in this situation, f strongly oscillates, all right? So now I will present an example. We know that the sine function is oscillatory function, right? So this result here provides conditions for a function, sine function, to be oscillates in the sense strongly, all right? Strongly oscillates. So consider the function f. Define this sequence here. It's possible to prove that f applied to minus t0 is equal to 0. This condition here is satisfied, and this condition here is satisfied. So by previous result, it's possible to prove that the sine function strongly oscillates, all right? So now I will use the results about pullback oscillations on linear evolution process to obtain results about pullback oscillations for solutions of generalized ODEs, all right? So let A be an operator satisfying the following properties. A belongs to the set, and this condition here are satisfied. So we consider the linear generalized ODE, and a function x is called the solution of the linear generalized ODE if satisfies this equality here, where the integral is the sense of Kurzweil integral. I will not talk about the generalized ODE theory and Kurzweil theory because Fernanda will talk about these theories later, all right? All right. I won't talk about now, about this now. So it's possible to prove that under previous conditions, the initial problem, value problem, admits a unique solution defined in R. And it's possible to prove that this solution, this unique solution, is given by this equality here, where EU is a fundamental operator satisfying this equality here. So it's possible to prove that the linear generalized ODE generates a linear evolution process because the fundamental operator is a linear evolution process because this operator satisfies these conditions here. That is, U applied to T and T is equal to the identity operator, and this equality here is satisfied. So the fundamental operator generates a evolution process, a linear evolution process. All right. So now we present the definition of the pullback oscillation for solutions of the generalized ODE. A solution X of the linear generalized ODE pullbacks oscillates at time t0 if for every linear functional in X star there exists S1 and S2 such that this condition here is satisfied, all right? So in this case here, we consider the number 0, but we can consider other value. For convenience, we take the number 0, all right? So we are in position to present the main results on oscillation for generalized ODs, and these results are direct consequence of the theorems obtained for evolution process and the fact that a linear generalized ODs generates an evolution process. So we have the following result. Let X be a solution of linear generalized ODE if this condition here is satisfied. So if X pullback oscillates at time t0, then this condition here is satisfied. And this condition here is satisfied, then X pullback oscillates at time t0. So the proof of this result is a direct consequence of the fact that EU generates a linear evolution process, all right? So now I will present the application. It's important to note that the class of generalized ODs encompass other types of differential equations, all right? So we investigate the existence of pullback oscillatory behavior for a class of abstract ordinary differential equations using the results about pullback oscillations for solutions of generalized ODs. Then consider the ODE here, and assume B is a locally Perron integrable matrix over R. Assume this inequality here is satisfied, and this inequality here is satisfied for a locally Perron integral function M. So a function X is said to be solution of ODE if X belongs to the set and X satisfies the equation true almost everywhere, right? So now the next result provides a relationship between solutions of generalized ODEs and solutions of the classical ordinary differential equation. A function X is a solution of the ODE if and only if X is a solution of the linear generalized ODE, where the operator A satisfies this equality here, all right? A is equal to this function here. The solution X is given by this, and EU is a fundamental operator, right? So now we can present the definition of pullback oscillate for solutions of abstract ordinary differential equation. A solution X of equation 2 pullback oscillates at time t0 if for every linear functional that exists a number t0 such that this inequality here is satisfied. So then it's possible to prove the following result. This result here provides conditions for a solution of abstract ordinary differential equation to be oscillatory, in sense pullback oscillation, all right? So consider the equation 2. Assume that there exists a number such that this condition here is satisfied and a sequence satisfying this equality here, and assume that this equality here is satisfied. So it's possible to prove that any solution X of the equation 2 pullback oscillates at time t0. So, for example, consider the matrix B here, where the function f satisfies the following situations here. Then, by theorem 6, any solution x of the abstract ordinary differential equation pullback oscillates at any time t0. Right. So now I will conclude my presentation with some considerations. If S applied to T and S is equal to this for all T greater than or equal to S, Then this evolution process defines a family of semigroups where T applied to T is equal to S applied to T and 0, all right? Let's remember the definition of semigroups. A linear semigroup is a family of continuous linear operators satisfying the following conditions. T applied to 0 is equal to the identity operator, and this equality here is satisfied. So, a point X strongly oscillates with respect to a semigroup now if for all T greater than or equal to 0 there are T1 and T2 such that this inequality here is satisfied, all right? So, it's possible to prove that following theorem. A point X strongly oscillates with respect to linear semigroup if and only if this condition here is satisfied, all right? For linear semigroups, the behavior of strongly oscillates is the same as oscillation in Pullback's sense, all right? And for a given linear semigroup, we define the following process. S applied to T, and S is equal to this. So it's possible to prove the following result. Consider X in set and S be an evolution process satisfying the following condition, all right? Then it's possible to prove that X strongly oscillates if and only if X pullback oscillates. Then in the case we have a semigroup, the definition are equal, all right? Because strongly oscillates is equal pullback oscillates. The result we present in this lecture can be extended to any class of equations that generate a linear evolution process. In particular, we prove in the paper oscillation theories for classical ordinary differential equations and Volta-Stieltjes type integral equations. That is, any differential equations which generate a linear evolution process. Then we have this result. This result can be applied to this situation, all right? So I'm nervous. Then I think I spoke too fast. I'm so sorry about this, but more time for the coffee, right? Thank you very much for your attention.
Any questions or comments?
I remember somehow, maybe I don't remember it well, that the GODE can be also written a special case, or let's say a dynamic equation on a time scale can be written as a special case of a GODE, right?
Yes. Time scales,
Difference equation.
delay differential equations, impulsive differential equations.
Okay,
there are
so-
other types of differential equations.
So what would be your results applied to that case? Because you didn't do that in that paper, right?
Sorry, it's,
You didn't apply your results in the paper to timescales.
no time scales.
Why? Just
But-
because you...
I can, but
There's no complication.
I don't know because I didn't work time scales, but Fernanda works time scales.
About the relationship of time scales and
I know it's possible, but
there is no complication. It's the same as when you place all the results.
Because we don't have this Pullback oscillation for timescales, and if it can be made in that way, good.
Yeah.
But, sorry, maybe somebody else.
No, please, you can.
But now I'm really wondering, like in the discrete case, we have some definitions with not less than, but bigger than. And since that contains the discrete case, what do I not understand here? like in Roman
I
story.
didn't understand. With the definition of composition of linear functional,
Yes,
you
yes.
say?
Then you can use the idea which came from that paper of Tabor. That can be used anywhere.
But in the paper of Tabor presents an idea of composition functional, but he's not work pullback oscillation. It worked pullback oscillation.
Just for, yes.
I wanted to ask, when you talked about linear functionals, did you always mean linear continuous functional?
Yeah.
Oh yes. All the linear operators, so continuous, linear, continuous, yes.
Any other questions or comments?
Marielle, does it make sense a definition of weakly oscillatory? It caught my attention the fact that your definition, private definition, involves a strong oscillatory behavior. Does it make sense a weak or minor oscillating behavior or not?
Strongly because all they're functional.
Yes.
Yes. All the linear functional satisfying this condition here. So the name strong.
That's okay. And second question, you can come back to the definition of oscillatory for Banach space.
Strongly oscillate?
No, the definition for your the definition of oscillatory for your equation for the process.
Okay, all right. This definition?
This one. Yeah. Again, does it make sense to have a mirror behavior in the sense of changing the parameters into the process or not?
I didn't understand. Repeat, please.
Okay, the definition says capital S of 0, S1, and then capital S at T0,
Yes.
S2.
Uh-huh.
Does it make sense to redefine capital S, S1, T0, and then capital S, S2, T0, or does not make sense?
Oh, yes, I don't have problem in situation, all right? I don't have problems.
Probably you will obtain the same results.
I believe that.
Oh, okay.
Okay, any other questions or comments? Okay, if not, so let's thank our speaker again. So now we have coffee break and then we back.
It's all very nice. It's nasty. I would have to be honored because sometimes go through.
Okay, so let's continue with our next speaker, Professor Fernanda Andrade da Silva. It's my great pleasure to introduce her. She's my sister, academic sister. And she will talk about modern perspectives on stochastic calculus on timescales. So let's see.
Thank you, Jacqueline, for the introduction. Also, I would like to thank all the organizers for the invitation and for this opportunity. It's a pleasure to be here at Campinas to give a lecture, especially in a celebration of At first, I would like to explain my title. It's a little different from the abstract book. So when I received this invitation, I thought about talking about the study, my research about stochastic equations that I have been developing for the last 4 years. But since we are in a workshop on dynamic equations on time scales, I thought maybe I can add some perspective of how we can put time scales in this new theory. So this is an idea that I'm thinking for a little time from now on, and it's going to be my next step in my research. So at the end of the talk, I will talk more about this. So modern perspective on stochastic calculus. This is a work based on previous and ongoing works with Everaldo Bonotto and Marcel Federson, both from University of São Paulo, Rodolfo Collegari from Federal University of Berlândia, and Tapper Gill from Howard University. So at first, happy birthday. This picture was taken in 2018. It wasn't the first time we met. We met 1 year earlier in Portugal in a conference there. You are an invited speaker. So we didn't meet in a bar, but I chose a appropriate photo because you're always with a drink. So you have mine.
Not always. But maybe I can say something because last year I went to Sao Carlos to a conference. But I arrived 2 days earlier and there was nobody there. It was kind of raining. I walked along in the road, first time in a foreigner city, and then I hear, Dr. Bohner! And she came out from the bar.
And I have another history about that conference. We book a happy hour, and I have a car in São Carlos. So many of the participants was going with me, and many of them are going to take an Uber. And since I was also asking a Uber for a group, I was staying for a long, and Bohner is supposed to ride with me, and he was. I'm losing like 10 minutes of drinking. Let's go. So this is the outline of my talk. Before I start to talk about the stochastic calculus, I would like to talk about generalized ODEs because it is a motivation. Okay. So first, I'm going to talk about modern integration theory. Then generalized ODE, stochastic calculus, and generalized stochastic equations, and some future research. So I'm going to begin with the Hainstock-Kurzweil no-absolute integration. So the idea of this new type of integral, it is the same of the Riemann sum. So the definition is very similar. The only difference is how we measure the length of the subintervals. While in the Riemann integral, the lengths of the subintervals are bounded by a constant, in the Kurzweil, they are allowed to vary more with a positive function. So this is a geometrical representation. So here I have a subinterval. I choose a point in this interval, which we call a gauge. A tag. And we say that this interval here is contained in a bigger interval of length measured by a function in this tag here. So formally we have x abundant space. U is a function defined from AB times AB into x. Is Kurzweil integrable over this interval here. If there exists an element such that given epsilon, there is a gauge, a positive function, so that for all delta fine divisions like this, we have this inequality here. So here we have like a Riemann type sum, okay? So let's see some specific case when I define u of tau t is equal f of tau g of t. So this sum, in the definition of the Kurzweil integral, is like a Riemann-Stieltjes sum. So in this case, we have that the Kurzweil integral is the Kurzweil-Stieltjes integral or the Behn-Stieltjes integral. And in the particular case where G is the identity function, we have the Riemann integral if the gauge is a constant. But if it is not a constant, we call the whole integral. So because this is slight different about the length of the subintervals, give us a lot of advantages. For example, we can consider an interval which is a union of a lot of intervals with a very small length. So because it's very small, the length, in the Riemann sum we don't have so many. So it continues to be integrable. An example is the direct function. So if we define the gauge like this, we are going to have that the function in the irrational points is 0, so it doesn't matter in the Riemann sum. Another advantage is to control points that our function is bad behavior. For example, this 1 over square of t. If t is bigger than 0, is t is equal to 0. You have a problem here. Okay? In this interval, this function here is bounded and continuous, so it is Riemann integrable. But here we have a problem. But if we choose a properly gauge, said that at the first tag must be 0, then f of 0 is 0, doesn't matter in the Riemann sum, so it is Kurzweil integral. Another advantage is that it improves some classical results. For example, the fundamental theorem of calculus that says, okay, we have a capital F differentiable, so that the derivative is equal to f. Then f is Kurzweil integrable, and we have the inequality, the usual equality here. Note that it does not require any additional assumptions in f, unlike the Riemann version, which requires f to be Riemann integrable, or the Lebesgue, which requires f to be absolutely continuous. More advantage, so with this new integral have every derivative, it is integrable, it's not absolute, deals with highly oscillation functions or unbounded variation, contain its improper integrals, which we don't have for the Lebesgue case, and generalize lots of convergence theorem. So every time that I say about Kurzweil integrals, it's more general than Lebesgue, and people that they are not used with this new integral say, really? Yeah. Are you sure? Yeah. So this time I decided to prove. So I'm going to prove that every Lebesgue integrable function is Kurzweil. So at first I consider a function like this, and I open interval containing a bounded and a compact interval. And C is the characteristic function. So we have this equality here. So the Kurzweil integral of this equation, this function here, is the length of the interval, which is the same of the Lebesgue. Well, if I take J as a union of bounded open pairwise disjoint intervals, then we have this equality here by linearity. Okay. Aqui finite, okay? The union is finite. Now if U is an open, then U is the union of decreasing open sets like IN. And I can define Gn like this, and Fn is here is missing a equal C of Gn. Then we have the assumptions of the monotonous convergence theorem, and we can apply this theorem to prove this. Now, if M is measurable, then there is almost everywhere intersection of decreasing sets of open sets, and again we use the same result to prove this equality for measurable sets. Since we are here, we are working with simple function. It's work for all measurable functions. Here could E, but it's M. Here I consider E a measurable set, but it's a subset of AB, so it's bounded. But if it's not bounded, I can consider En like this intersection here. This is a measurable set, it is bounded, so the results work here. E is the union of this En, and you can use again the convergence theorems to prove that works for all measurable sets, and you can extend to Rn. So in fact, every Lebesgue is Hengstad-Kurzweil integral. But every Hengstad-Kurzweil integral is Lebesgue. So let's see. And this is an example, so I consider a function like this. I'm going to prove that G is Kurzweil integrable, but it's neither Lebesgue nor or a Riemann proper. So this is the graph of this function here. So it's not bounded, it's not absolutely integrable, so it's not Lebesgue. Actually, it's a Riemann proper. EG is this function here, plus H, where H is a direct function. So I sum a Lebesgue, which is only Lebesgue, it's not Riemann, with a Riemann proper, which is not Lebesgue. So it cannot be either Lebesgue or Riemann. But it's Kurzweil because we can apply the fundamental theorem of calculus to calculate the integral. So actually it's bigger. So I like, okay, this is a very simple example because I take one of one group, another of the other one, sum of two of them. Of course, it's neither in one set, but can every Kurzweil function be written as a sum of Lebesgue and Riemann proper? And the answer is not. The example is not very simple to say, but it is in this paper here. So, Marielle demanded me to talk about generalized ODEs, and I was intended to do this because it is a motivation of my work. So, the solution, a function, is called a solution of this equation if we have this equality here, where this integral here is the Kurzweil integral defined by this. So what basically I do is to work with equations, can or not can be differentiable, but the solution is an integral equation, and the integral is considered as Kurzweil. Let's see some properties about this equation. For example, we have H, a non-decreasing function, and you say that F belongs to this class if you have these two inequalities, which is like a Lipschitz and a characteristic types ones. And if F is regulated, this means that the one-side limit exists. So if F belongs to this class, then the solution of the generalized ODE satisfies these two inequalities here. And it is regulated and it is continuous in each point that H is continuous. Also, it is of bounded variation. So for the existent and uniqueness result for the solution, we have that if F is in this class, we have that the initial point doesn't goes away from our domain, then there exists a maximal solution of the generalized ODE with an initial condition. So Marielle also said that generalized ODEs encompass lots of equations, and it in the sense that we have an equation and a generalized ODE, and there is a one-to-one relationship between the solutions of our equation and a generalized ODE. So why this is good? Because if I prove a result here, I can use this relationship to translate this result for generalized ODE for the equation. As the same as properties or definitions. For example, Marielle said, oh, the solution here is oscillatory if blah, 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 blah. You can define like time scales. The time scales, the solution is oscillatory if the solution of the corresponding generalized ODE is. Maybe, I don't know if it will make sense or not. But when you have this, so if I work with stability, the solution here is stable if the solution here is stable and we have the inverse too. So we can go in for lots of times. Of course, each concept has your own problems. So this is all the types that you have. Another thing, because we have this, we can translate our result. The theory of generalized E acts as a unifying theory for many equations. And it has been very relevant. For example, it was included as a classification, a mathematical classification. Also, since the solutions of generalized E's are described by the Kurzweil integral, and the Kurzweil integral is bigger than Lebesgue, we can consider more functions in our equations. So, acts as a unifying theory, and we can go on with our functions. Let's see some examples. Here I consider ODE, a classical ODE. So the solution is given by this equation here. So this is the Riemann integral. So it can be approximated by this Riemann sum or this sum here. When I define capital F as this integral here, we have this difference here is equal to this integral here. So that by definition, the Kurzweil integral of this function f is the Riemann integral of f. So if we have a one-to-one relationship between the two integrals, we have a one-to-one relationship between these two equations here, which are solutions of our equations. So it is solution of our classical D, even only if it is a solution of generalized D. And we can do this for example, measure function differential equations, which are equations like this. We define capital F like this. This is a great book who wants to learn about generalized E's. The author is Obada Prize. And let's talk about time scales because we are in time scales event. So some notations, be it a time scale, I define TK like this, where Ho is the backward operator, and this is the definition of delta differentiability, everybody knows. So F is regulated if the right side limit in all right dense points, and its left side limit exists in all left dense points. And if F is regulated, we have this fundamental theorem of boundaries here. So before, I said the Behoen-Stutes integral is a particular case for the Kurzweil integral, and it is given by this Riemann sum here. And the partition is like this. So in a classical real analysis, we use symmetric neighborhoods like this. But when we are working with time scales, this maybe is not possible. It's not always possible. For example, the neighborhood not exist. For example, if we have a left point C, and C is the minimum of T of our time scales, or we don't have this space here, the length is smaller, I don't know. So that's why you need an adaptation of the definition of delta partition. So we say that delta, now it's actually two functions, is a delta gauge if we have all the partitions here. So we say that D is a delta fine tag division if we have this inequality here. So as before, we have the same delta, the same gauge. Now we separate with two different gates. So with this two-side gauge, delta L controls how far left from the tag C we are about to go, and CR controls how far right we can go far from C. Also, this defines like a asymmetric neighborhood like this, but it's more flexible and appropriate, especially when our tag is left scared, right scared, or it's very near to the boundary of the interval. This condition here is very important too, because ensure that the tag of our partition does not extend beyond the forward jump operator. This is essentially time scales, especially when we are considering wide scared points. Here is an example, like we cannot have type 1 bigger than sigma of type 1. Because this would allow to include point in the subinterval that does not exist. So I give an example. So I consider T like the integer numbers, and this interval here, which is the set of 1, 3, 4, 5. And I consider a division given by this. So
2, 3, 4, 5, right?
yeah. Thank you. So since sigma of C is C plus 1, we have that the greenness operator is given by 1 always. So we have this inequality here. So the first gauge, the right gauge, must be less than or equal than 1. Also, we have this inequality here. With this inequality here, we have that the right gauge is 1. On the other hand, the left gauge is need to satisfy this, so we can consider any positive function. Okay, with this adaptation, we can define delta Perron integral, which is the same definition as the Perron integral, but we are considered delta gauge instead of gauges. And it's clear that every delta Riemann function is also a delta Perron, every delta Lebesgue is a delta Perron, but the converse is not true. For example, I consider these timing scales here, and f of t is 1 of t, for t bigger than 1, and 0 for t is equal to 0, or t is equal to 2. It's not delta Riemann integrable because 1 over t becomes unbounded near to 0. Let's say the Riemann sum over the partition near 0 diverges as the math gets smaller. But I can define the right gauge like this. So on this interval here, this gauge keeps the tags away from 0. So 1 of t is not bounded, it is bounded on every semi-interval. Also, this gauge keeps the interval inside of 0, 1, and this is true as required. Also, I can define the left gauge like t of 2, so we have this, all of the conditions are satisfied, so it is good to enter. Here we have that this Riemann sum converges to 1. So this integral here exists in the sense of Perron, and it is 1. Also, we have a relationship between the Perron delta integral and the Perron integral, and it's given by an extension of our function to find on a time scale. So we have a time scales, an extension of this time scales, and function, and we define the extension of this function by this. And we have that the Perron delta integral exists if and only if the Perron integral exists and both are the same value. So because we have a relationship between these two integrals, the same as the classical ODE. I showed that we have a one-to-one relationship between the Riemann integral and the Kurzweil integral. So we have a one-to-one relationship between the integral equations, so the solutions. And now we have the same. We have a relationship between these two integrals. So we're going to have a two-to-two relationship about the solutions of time scales in generalized case. Now let's talk about stochastic calculus. The motivation is price of financial assets that varies over time or investment portfolio. The construction of the integral is very similar to the Lebesgue. So we consider f like a simple function, and we hope that the integral of this f is the length of the interval per is the difference of the Brownian motion. So if you have a function f, you write it like a linear combination of simple functions, then we hope that the integral of this function is given by this. And if we have a sequence of simple functions that converge to a function, so we hope that the integral of this function, the integral, is the limit of the others one, the simple ones. So the construction of the integrals involve Lebesgue's tools. And that's why we have a similar necessary similar sufficient conditions, which is it has to be a mean square integral. The expectation of the mean square integral is finite. So here I have the Riemann sum, okay? And the question is this Riemann sum or the Kurzweil integral suitable for stochastic calculus? So let's see. I define u of tau t is equal f of tau b of s. So the Riemann sum in the Kurzweil integral is this. Okay. But here I have a problem in the stochastic calculus because tau 1, which is the tag of our division, can be bigger than ty minus 1. In the stochastic, it doesn't make sense because we are working with probability and we only have information until ti minus 1. That is the ft I minus 1 measure. So, because of this, we need to consider tau e smaller than ti minus 1. So that's the concept of belated partition. So instead of consider like intervals here closed at the beginning and attack in some point here, we consider left open intervals, and our attack is always the left point, the beginning point. Also, we don't consider anymore a full partition of the interval. We consider a partial division of the interval. But we ask that the parts that we left off the divisions has the length smaller than an eta. So this is the formal definition. Again, we have a gauge. Look here that we can include 0. In the Kurzweil, we don't have this. A non-negative function, and we have a interval pairs, a point interval pairs here. And we say that this is a delta belated partial division. We have this equation here. So why you can have 0 here? Because if it is 0, this equation here doesn't make sense. We don't have these points, but it doesn't matter. It's a partial division, not a total division. Note that given any non-negative function delta, one may not be able to find a full division that covers the whole interval. For example, this function here. But the interval but by the Vitali convergence we have that for every non-negative function delta exists a delta-related partition and a cover of this over a small positive measure. This means the parts that we left off has length less than it, and we always can do that. So what Marcio, Rodolfo and Tapper did in this paper here was, okay, for the continuous case, we have generalized E, which is considered solutions of equations described with the Kurzweil integral. But now for the non-discrete case, the stochastic case, we can have the same thing. I mean, we can consider equations or process where the solutions are described by a more general integral than Ito. So they define what they call Kurzweil-related integral, which is practically the same as Kurzweil integral, but now using related partial divisions. Okay, the definition of the Kurzweil-related integral is based in the LP norm, okay, which imposes a probabilistic control over the approximation terms. The tolerance of eta allowed in the remainder of the divisions enables the construction of approximations that converge in the expectation if they are not pointwise accurate. In particular, while G is not in LP pointwise, the overall sum converges to an integrable limit K in LP. As a result, G can be explosive or have infinite points. Also, we have the relationship between the Kurzweil-related integral and the Ito-Stock integral. The Ito-Stock integral is a simple reformulation of the Ito integral using Riemann sum. So we have this equality here. So again, since the Ito-Stock integral was constructed like the same thing as Lebesgue, we have this restriction here. But for the Kurzweil integral, we have that G is not in LP, so maybe this is not good for us. Okay, this is equal to this, it's the same, okay? It's a different formulation. But the Kurzweil-related integral seems like bigger than the Ito-Stock. Verada and I are working with an example right now, so hopefully we finish soon. But we believe that, in fact, it is bigger. So new research field became called generalized exponential equations, which is the same as generalized E. So we say that a process is a solution of this new type of equation if you have this integral equation here, where the integral is in the sense of Kurzweil. So when you consider a Cauchy problem, we have x of LP, this norm here is this expectation. And as a generalized D, a sufficient and necessary condition for the existence of solutions of generalized stochastic equation is that our function belongs to a class. And the class is almost the same, but now we have the expectation. Okay, if it belongs to the class, then exists a local solution. Also, we prove that if f belongs to this class, then it is continuous in the exploitation. So what we did was, okay, we have a solution in an interval and another solution in another interval, but the final point here, the final value here, is very close to the first one. We can glue these two solutions, these two functions to obtain a new solution. It's the same for classical ODEs. So using this, we can prove that there exists a unique maximal solution. Also, they prove that there exists a one-to-one relationship between classical ones and generalized ones, but here only classical. Okay? Some properties, as I said before, the solution is continuous in the expectation, but when we are in the classical theory, we have that the continuity of the solution is almost everywhere. This means that this function here is almost everywhere. And the first question is the same? These two properties? And the answer is no. Here, I consider this process here, okay, where y of t is t over power alpha, where z is a random variable, okay. So this function here is continuous almost everywhere, but is not continuous in expectation. On the other hand, if I consider u as a uniform random variable and consider this process here, so this function here has a jump from 0 to 1, so it's not continuous almost everywhere, but it is continuous in expectation. So neither of them implies others. More results about these equations you can find in these two papers here. And let's talk about future research. So what we have in the literature nowadays is time scales equation with non-continuous term here. So the solution is given by this integral here, where this integral here is the delta Lebesgue, and this is the delta Ito. So this integral here is defined like this. So we have condition like the Lebesgue, like the Ito, which mean square integral. So the probability of the mean square integral is finite, is 1. As I said before, in the continuous case, non-stochastic case, we have the Behon delta integral, which we have an adaptation of the division for the Kurzweil, but now for the time scales calculus. And we can consider the solution where this first integral here is the Behon delta integral. My idea is to think about this adaptation on the Kurzweil related integral to define a delta Kurzweil related integral and consider a stochastic dynamic equations on time scales and stochastic dynamic equations on time scales where the solutions are given like this. So this is my next step. And also prove a relationship between this new time and the generalized stochastic equation. So that's it. Thank you.
Any questions or comments?
What's even the definition of the Wiener process in time scales?
And that is a problem because
I mean, you wrote down delta WS, so what does it mean, the W? Is the W just the normal?
This is the annotation, okay? This is the Wiener problem in the normal case because we are considered continuous.
So you only use the normal Wiener process?
Yes. This is actually yours.
What?
This is actually yours.
So my first PhD student worked on that, Suman. There are some papers, but only for isolated time scales. Yeah. So once you get the results, you can compare whether they're the same, at least in our paper.
And that's the idea. I didn't start.
Yeah.
Any other questions or comments? have just one comment because Martin asked in the Marielle's talks about the relation with time scales and generalized OD. Then Fernanda brought here the correspondence. But I think in the case of Marielle, it's a little different because it has a process there. So in that case, it appears some exponential function. And I believe that's not so directly to have something for time scales because we cannot relate the exponential function, even with the integral with measure with a time scales. We need to use some general exponential function that Monteiro and Slavic, they introduced some generalized exponential functions and the generalized trigonometrical functions. So just using that general exponential function, that's possible to relate with the time scale. So I believe that maybe it needs to change a little in order to have those correspondence. But all of these comments. Okay, any other comment or questions? Okay, if not the case, thank you very much. Oh, sorry.
How about Ito rule? Do you have an Ito rule in the general case?
Do you mean like by Ito rule?
Ito rule, like the chain rule in stochastic calculus.
We have Ito isometry already.
Yes.
But we have to prove it.
Yeah.
Like for the
Yeah, because if we want to get the Ito rule in the time scales, we first need to have it in the big plot. Yeah. Or S plot. What is it called?
So the isometry we already have. So
yeah.
For the Ito is the same. The Ito is the same. So we know that the calculus work with this sum that they define.
No, Ito isometry is something else. I mean, it's the chain rule in stochastic calculus. It's called Ito lemma, I think, or Ito rule.
Okay.
Yeah.
I don't have that.
Okay.
It's a lot by the persuade related percent, and then translate this times cases.
Okay, any other questions or comments? Okay, I don't think so. So let's thank Fernanda again. Thank you. So it's my great pleasure to introduce our next speaker, Professor Paulo Henrique Costa. Actually, we were colleagues in the undergraduate studies, and he works in my previous university. Now he is the chair of the department in the University of Brasilia. And today he will talk about ergodicity bounds in the sliced Wasserstein distance. So thank you very much, PH. So the floor is yours.
So thank you very much for the introduction. I also would like to thank you, the organizers, for this very nice event. I'm pleased to be here celebrating the Martin birthday. I first met Martin about 10 years ago. He was visiting us in Brazil, and since then he was there many times.
All the time. But what about from now on?
We share many years of being together with Jacqueline. And as you know, in this special configuration, it is always gonna be time. So, thank you. So I'm going to talk about this recent joint work with Professor Gerardo Barreiro from ISD in Lisbon, Portugal. Also with Professor Michael Hogli from University of Los Andes in Bogota, Colombia, and we established some ergodicity bound in Wasserstein and slice Wasserstein distance for true stable autoregressive process. And let us start with some kind of toy model, very simple, just to get some ideas. We consider here. We consider this model here in one dimension, and Q and sigma are just real numbers. Q has absolutely value less than 1. The noise here is modeled by a standard Gaussian distribution. In this case, we can compute the distribution of the process xt and also the limit distribution. It's not that complicated. And the most interesting fact here is because we can compute explicitly the Wasserstein distance of order 2. In general, this is a bit complex, but here we can compute. And so we have this kind of Pythagorean formula here. And if you look at this expression here, we have this kind of two-scale phenomenon, because in the mean we have this kind of velocity, and with the variance we have 2 times faster velocity. Then the natural question is what happened when we increase the dimension, when we drop the Gaussianity, and also when we consider higher moments in the Wasserstein distance for some moments different than 2. So we want to know if this phenomenon survives when we do that. And my work today is to try to convince you that it's a nice, interesting problem, and it's not trivial. Let's see if I can do that. So, what's the problem when you consider this kind of scenario? When you increase the dimension, we introduce in the system some complex geometry, like you allow Jordan blocks, and this change a bit how the dynamical system behave. When we consider Wasserstein distance or slice Wasserstein distance for order G different than 2, we lose the closed formula, so we don't have this nice expression. And when we drop the Gaussianity, we lose the nice and explicit formulas for the distribution. So in this scenario, we are completely blind. We need to develop some new tools to see something. That's the problem that we want to solve. The general model is given by this multivariate autoregressive process. As you can see, it's very similar to our first example. We just change the real numbers for the matrix Q, and here we have some kind of covariance matrix. And the noise here is it's a general noise at the beginning. We can get the pathwise representation just using some induction in this noise here. Probably many of you are familiar with this kind of system. That's not a new model. Generally, we see this model as with this companion matrix, it's standard, and also with the standard Arnold process. So this model is not new. What is new is a tool that we introduced to get the bounds. So that's the idea. Sorry, but you are here that it's not used to use the microphone. So what we need to try to recover this two-scale phenomenon. So first we need to structure a hypothesis. The first one we call true stability, meaning by that the spectral radius of the Q matrix is strictly less than 1. And also we need some integrability of the noise, this condition here. And if we have this both conditions, we can guarantee the existence and the uniqueness of the invariant stationary measure. So, one point here that's nice is the fact that the spectral radio governs the dynamic system, but this is not enough to get the bounds because it does not generate a submultiplicative matrix norm. So we need to construct some appropriate norm to get the bounds. And to fix that, we need to use a Schur decomposition that provides what we call Schur norm. And this norm is parameterized by this kappa star constant. And here we have some technical details. I'm not into these details, but the important fact here is that all of the constants that we have here are explicitly computable. So we know how to compute every constant that we have here. From the theoretical point of view, this is not that important because we can prove the theorem without knowing exactly how are the constants, but we have a bit more. We know how to compute the constants. From the applied point of view, to know the constants maybe can be important because this is more or less saying to you how long you have to wait until see something when you're running your simulations. And that's the idea of giving the explicit constants. So, with this in mind, we want to compute at least find bounds for Wasserstein distance and also for the sliced Wasserstein distance. As you can see, the Wasserstein distance has this standard definition here. And for moments bigger than 2 is a beautiful problem, but from the applied world, it's a nightmare because for how do you say to the computer to get this number if you don't have a closed form? So generally you need to use some kind of linear program, and the problem is the order is big, so you have to wait too long to see how is this number. So if you can see nothing here, you can use the side that's much more simple. So what is the sliced Wasserstein distance? Basically, we get, you just take the distributions, project in the direction v, that is in this way, and then you sum all of this distance by integrating on v. So it's some kind of average that give you some information about the Wasserstein distance. So that's the idea. From the applied point of view, it's much more simple to implement because this computation is just in one dimension. So the price is low in the original Wasserstein distance. So that's the idea. And that's the reason why we compute the bounds also for this lesson. Going back to our initial case that we want to recover this 2-scale rate, we need to impose some very restrictive condition that we call here by periodic interpolation. This is basically saying that the process xt is an affine transformation of the limit distribution. We know that this works for Gaussian and alpha stable noise. In dimension 1, it's just what we call by the self-similarity. And the problem is, this fails for a very simple example that we call Hadamard noise. And for any discrete noise, that the autoregressive process has limit a continuous distribution. So you can consider that, but there are some limitations that you maybe need to solve after doing that. So with this definition, we can recover this nice 2-scale phenomenon. We can prove this affine transport estimate that's given like that. And using this lemma, we can prove the phenomenon that I said in the first slide. As you can see here, the Wasserstein distance of order P has a noise term in the mean term, and this property covers this nice true-scale rate. Of course, here you cannot see that, but if you use as the noise the standard normal Gaussian distribution, we can see exactly more or less the same behavior that we had in the 1D dimension. This term here, it's with the show norm, has disorder Q. Here we have a very big effect, but the important is this variance correction has this way. It's double fast, so we have exactly the same behavior as in the simple example. And if you apply this result in Wasserstein, in sliced and Wasserstein distance, we have the same behavior, just in one direction V. Here, if you project in the process and the limit process in a special direction V, in the generic direction V, we have the same behavior. This term will have the velocity norm of power T and a big effect, but here we have a double velocity. So in this scenario, we have the same phenomenon. Also, if we integrate or over the V over this field, we also have the same phenomenon. This lower bound is just this bound here, repeating the side. So we have, in this case, also this just phenomenon. So that's a nice fact that we can, in higher dimension, recover this problem. But as I said before, we don't know if, of course, this the condition that we call by ergodic interpolation is quite restrictive. If you have a very simple example that is Haber-March noise, basically you can think, for example, that you have a particle jump for 1 to minus 1 with probability for off. If you insert this noise here, the autoregressive process has as limit the uniform distribution from minus 1 to 1. And of course, there is no way to this process be an affine transformation of that because we have a topological incompatibility. We cannot have this property here, and it's a very simple process. On the other hand, for this process here, we can compute explicitly the Wasserstein distance of order 2. And as you can see, there is no additive term. It's just some kind of multiplicative noise. So we need a different result for this kind of process. And fortunately, we can prove the bounds using just the hypothesis 1 and 2. If we consider generic noise, we can also provide the bounds for the Wasserstein distance of a generic order. And here we can see that we have two different bounds. Of course, we can consider the mean of them, but we left it that way because the way that you compute it's different. The techniques for each of them is different. The first one.
Oh, sorry, can I just ask something? It's written t greater than or equal to 0, right? In the first line. T greater than t. Just, no, where it is. The first line, t greater than or equal to 0. Yeah, in the end, yeah.
Ah, yeah.
But is t integer or is it not?
It's integer.
Integer.
Yeah.
So 0, 1, 2, and so on. Okay. Yeah, just so.
Yeah, it's from the autoregressive.
Yeah.
Okay, so here we have this the upper bound is this or this. You can consider the minimum of them. And well, we let that way because the techniques are different that you get any of them. The first one, we can combine Markovianity with synchronous coupling. The second one, we just apply the Minkowski inequality in the pathwise representation. So it's different techniques we use to get the different bounds. Of course, you can use what's the best fit for your program. Just one more. So when we are looking to this term, there is something interesting here. So if the matrix Q is diagonalizable, this factor will have a pre-exponential rate. If the matrix has complex eigenvalues, you will see some oscillation. And in the case that we have Jordan blocks, will appear here in the rate some polynomial. So you can see in this case some transient growth before the decay. So that slide is special from the applied guys. I don't know if there's some here. It's basically saying that if we run in parallel any copies of any independent copies of a Markov chain, the error of the joint distribution is bounded by the square root of n times by the error of a single Markov chain. So this is basically saying that running in parallel does not make your system slow. It's a nice result. The perspective of applications. And so now I want to show some visual numerical validations of the bounds that we get theoretically. And so the numerical test that we do was in these examples, R1 gradient system with diagonal and symmetric, with Jordan blocks in 3 and 4 dimensions. In the case of oscillation that is provided by complex eigenvalues. And also we compute the Wasserstein, actually the sliced Wasserstein distance in order 1, 3, and 4. So that's the example that I'm going to show to you. So maybe let me just write the matrix we made. So for the first example, the matrix is that one. So for the first example, that is the companion matrix. And if we compute the eigenvalues, we can see that is approximated as values here. We are considered this Wasserstein distance project in the direction V, this particular V, and this is the initial condition. So here we can see that in the beginning, the dot blue lines is the actual Wasserstein distance project in the direction V. The red and the green line are the theoretical bounds. So in this example, we can see that the lower bound is better than the upper bound. For the second example, that's not clear at all, but I guess you can see more or less the pictures. So here we consider the gradient system. I don't know if we write. Well, let me just write the matrix. Because here it's interesting because the both systems share the same eigenvalues, but the matrix are different. That one is just diagonal, and the other one we have a full matrix. So side, it's just like this. So that is the left side. The right side, the system has this way. One. So in the right side has this matrix here, and they share the same eigenvalues. So you can see that they have a similar behavior, and it's not that different. So what really matters is are the eigenvalues true? So the next example, I guess, is one of the most interesting because we have this behavior for the Jordan blocks. As you can see in the first example, we have some small eigenvalue, and then if we have a fast decay. In the second one, we have a big eigenvalue, and then you can see the stress before the decay. And that's the difference between this example that I showed in the previous slide, this transit phenomenon. There is something here that's also interesting. In this case, the upper bound at the beginning is better than the lower bound, different from the first example that I showed, so that's also interesting. The next example, we consider some oscillatory dynamics that comes from some complex eigenvalue. I'm not writing down this matrix, just the matrix has this complex eigenvalues. And then we can also see that the actual distance, it's okay with the bounds, also in this situation. Now, we consider a Jordan block in 4 dimensions. So it's 2 Jordan blocks. The first one has this eigenvalue, the second one has this eigenvalue. And then we can see that we have here the slice versus time distance projecting this direction. And again, the upper bound is better than the lower bound. That's not happening in the first example. So more or less you can see that when we have a Jordan box, generally the lower bound is better, at least in our experiment, than the upper bound. And we use this same example to compute. Here is actually the fastest time distance in order 1. You can see that's very similar. And also we stress the system by increasing the order of the fastest time, the slice fastest time distance, not that big, just 3 and 4. And again, we can see that's the result is very similar to the previous slide. So that's what we do for this numerical experiment. If you want to see how we get that, it's available in this GitHub. You can see how we did these pictures. And just to conclude, what we did here was, so we find bounds for affine transport estimates. We introduced this called biparabolic integration we give some result for generic balls. That means you have some generic noise, then you can also compute the Wasserstein balls. We saw what happened when you have Jordan blocks and also with big eigenvalues. And from the applied point of view, there is this result that's nice. And in the end, what we have is the following. When we have this interpolation that is known in one dimension as self-similarity, we have this nice phenomenon that is additive to scale of the noise. If you have a general noise, in general you have just an exponential ball. It's multiplicative and not some additive things. So that's the idea. It's a short talk. I don't want to enter in the proofs because I guess it's a bit different from the talks that I saw today. So it's also concise. And that's all. Thank you very much.
Thank you very much. Any questions or comments? I have actually one question. Martin asked about that T that you mentioned that is integer. Is that possible to do that in another domain, like maybe time scales or something?
I guess not in the Curators, but at least isolated.
Yeah.
Because all your step size is always the same. Okay, sometimes bigger, sometimes shorter. But can you make it with varying step sizes?
Probably yes, but I'm not sure. I don't know if you were thinking about the time scale because in the Wasserstein distance can be very complicated to manipulate. I don't know.
Yeah. I mean, nobody's interested in this, I'm sure. That's why they're doing it. But you know, if nobody's doing something, then it's good to do it.
Yeah, I guess it's possible, but it's difficult. Because I guess you need to split in any kind of scale and maybe some, I don't know.
Yeah. Oh, okay. Thank you. Any other questions?
Hegel is not from Colombia, right?
No, he's German.
Yeah.
Okay. Any other question or remarks or comments? Okay. If not the case, so let's thank the speaker again. Would you like to have a break or should we go directly? We can have 5 minutes break if you prefer, or
It's the last one.
it's the last one. So let's do it. Okay. So it's my great pleasure to introduce our next speaker, my academic brother, Professor Edward Stone from Universidade Federal de Juiz de Fora, here in Brazil. And today he will talk about spectral decomposition of HSRN applied to the asymptotically linear fractional Schrödinger equation. So, Edward.
Thank you for the presentation. Thank you, Jacqueline, for inviting me to be here. It's a great pleasure to see Martin again. I think it's been 8 years we don't see each other. Martin is a brilliant mathematician and a great person. Fortunately, we don't have any works together. And I thought that we didn't have any pictures together.
Oh, yeah.
Yeah, but Fernanda.
Bauhaus and choose the forum.
Yeah, but I couldn't find it. And Fernanda completely destroyed my joke because she put a picture in which you are here and I'm here, right beside you. But I thought that the only picture that we had near each other was this one in Brasilia, and you are here and I'm here. So what I did was to ask to ChatGPT if he knows you. He of course knows me because I talk to him a lot. And I asked him to make some pictures of us. So he made this. Okay. I think that almost everything here is possible to happen. So maybe in a parallel universe there is a conference with lots of Martins and lots of me's, maybe. But I think that this one is not true.
Yes,
because we absolutely can't be working at 3:17 a.m. drinking coffee. So that's the one which is not possible. Okay. So
no, but there is a picture of us in this Inchois de Fora when I was there. There used to be a German brewery called the Brauhaus.
Yes.
It opened in 2001 and it closed a few years ago.
He knows more than me about this bar.
There's a picture of you, me, Olympio, and who is another student of Olympio?
I don't remember. Oh yes, I forgot his name. Yes.
Yeah.
Yes. And I think you liked very much this bar.
Yeah.
No, this is a great beer. Now it's called Prost.
Yeah,
yeah. So happy birthday. Happy birthday. I think I'm a strange person because I work with generalized ODEs. I work with time scales, and I'm on a conference with Martin, and I'm going to talk about partial differential equations. This is because this is my last submitted paper, and it is in collaboration with a former master student, Cesar B. So let me talk a little bit about the Schrödinger equation. Time-dependent Schrödinger equation is given by this equation here, and it describes the behavior of particles under the action of a potential V, this potential here. We are interested when V varies little over short time intervals, so we can consider that V is constant on this variable t. And if we look for solutions of this type, the spatial part of the time-dependent Schrödinger equation is reduced to this elliptic equation here, where this is the energy of the particle in the state described by the function u. So we want to complicate the problem, and we introduce a nonlinear term here, and we call this the nonlinear stationary Schrödinger equation. This potential V plays a crucial role on the existence of solution, and one of the directions that we can study is the spectrum of this operator here, with the domain on the Sobolev space A2. Also, we can consider the fractional Schrödinger equation, time-dependent fractional Schrödinger equation, and it arises naturally from the expansion of the Feynman path integral when applied to the Brownian problem. This is the fractional Laplacian, and it's defined like this limit of this integral here. And once again, we can consider the stationary version of this equation, which is where we are interested in studying the existence of weak solution for this equation here. I will start putting the set of hypotheses on these functions, but I will recall it later. So we consider this function g, this nonlinearity here, as this product of a function depending on x and another function depending on s. This function h is bounded function, which is also on this Lebesgue space for q being this exponent and p on this interval, positive function, f being a continuous function which has this behavior at the origin, and we consider that there's a positive a such that this limit at infinity is a over 2, where this f is the integral of the function f. This is why, I will talk about it later, but this is why we call this problem asymptotically linear. Also, we ask for this kind of compactness condition. We define this function q like this. We ask that it is positive and has limit as infinity. And in what concerns this potential v, we ask that it is continuous and it possesses a positive limit at infinity. Also, we ask that 0 belongs to this spectral gap of this operator, which we call from now on as SS. Okay? As I said before, this is a submitted paper with Cesar B. And the outline of this talk is mainly about the composition of the space HS. The main work was to study the spectral theory for this operator, present some properties of the spectral properties such as the location of the spectrum and the essential spectrum. We constructed this operator using since this is a self-adjoint operator, I'll talk about it later, and we showed this an equivalence of norms, and so we can decompose this space HS like this, and once we decompose this space like this, we can apply a linking theorem due to Suarez and Eliane Meyer. This may be a coincidence. I said that the last time we saw each other was 2018 in Brasilia, and it was the first time I saw this paper by Mayra and Eliane, because Mayra was presenting it. And I asked some things, and I had some ideas, and I started working on this type of problems. So let's talk briefly about the fractional sublab space. We consider this S on this interval, P on 1 plus infinity, omega subset over n, and we define the fractional sublab space as this set of functions which belong to LP, and this quotient is also on LP. And we define a norm on this space like this, and this term is usually called the Gallardo's seminorm of the function U. Also, given U on this set and S here, we define the fractional Laplacian acting on this function U by this limit here, as I said before, where C and S is a constant which depends on N and S, and is given by this, and PV here is the Cauchy principal value. Some properties, I want to show these properties, it's known, that this space, when we consider here P equals 2, this space is a Hilbert space, and for S on this interval we have this continuous emitter, so we can have this 3 here, which depends on S and M. So for fixed S here, we consider a potential, a bounded potential, and we define the fractional Schrödinger operator by this here. And we can show that the fractional Laplacian is essentially self-adjoint, and so when we refer to the fractional Laplacian, we mean the self-adjoint extension defined on this Sobolev space H2S. We need to define what we mean by a weak solution. We say that a function U on this space, first of all, for S given, we have that H2S is the domain of this, the fractional Laplacian, and so HS is the domain of this fractional Laplacian here. And so we say that a function U on HS is a weak solution in C0 infinity of this equation if we have this equality here. I don't know if it's well written here, but we have a parenthesis here and here. For every v on C0 infinity. Some auxiliary results and properties is that if f is on L2, and we have that u is a weak solution on this sense of this equation here, in C0 infinity, then in fact u is on H2S, and moreover u satisfies the equation almost everywhere in Rn. Also, if the potential V here, if the potential V is 0, then the point spectrum of the operator is empty. And also that if V is 0 as a consequence, if V is 0, then the spectrum of the operator is only the essential spectrum of the operator. Just to recall, maybe it's obvious, but to recall the definition of spectrum. We have a linear operator. This set is called the resolvent set of T, and the complement of this set is the spectrum of the operator, which we can divide into two parts. So the point spectrum, which are the eigenvalues of the operator, we have the discrete spectrum, which are the isolated eigenvalues, and the complement of the discrete spectrum is called the essential spectrum of the operator. So I put a little short proof from this fact that I said before here, that the point spectrum of the operator is empty. It's really short, so the important is a lemma which we made before. So if we take u on the kernel of this operator, we have that this is satisfied, and for every z on C0 infinity, from the self-adjointness of the fractional Laplacian, we have this equality here, and so from this regularity lemma, we have that this equality holds almost everywhere, where this is the Fourier transform of u here. And so this must hold almost everywhere, and this holds only if u is 0 almost everywhere. So the kernel is 0 for this operator, and so we have the result. As a consequence, we have that the spectrum is indeed only the essential spectrum when v is equal 0. It's important to... I hadn't thought about this before. I was on a conference and someone asked me, this also happens when v is increasing to 0. So this also happens. So when v is 0 or decays to 0, we have only really continuous spectrum from 0 to infinity. So let's locate the spectrum now. We consider this number lambda as this infinite here, and for every u on Hs with L2 norm equals to 1. And we can show some properties of this number lambda. We have that lambda is in fact bounded by below by this number here, calling that v is a bounded function. Also, we can calculate lambda on this way here, so we can calculate it on functions, on C0 infinity functions instead of functions on Hs. We can calculate it on this way, and also we have that if u is on Hs with norm 1, and lambda verifies this, then u is on H2S, u is on the kernel of this operator here, and lambda is on the point spectrum of the operator. Now we can locate the spectrum. So if v is bounded, then we have that the spectrum is contained on this interval, where lambda is that number that I said before. Lambda is on the spectrum of the operator. Also, for every lambda on the resolvent of the operator, this operator here is non-compact compact, and the essential spectrum of the operator is non-empty. So the spectrum and the essential spectrum are never empty, and the infimum of the spectrum is well defined. Now we locate the essential spectrum. So given a bounded potential, we define this number L as this limit here. We need, I won't prove it here, but we need a key lemma that if this limit is 0, then this multiplication operator is compact. In fact, this operator is defined on L2, and we are saying that M restricted to this space is a compact operator. And so we can locate the essential spectrum. If it's bounded, then the essential spectrum is contained on this interval L, where L is this limit here, L plus infinity. And as a consequence, we have that the discrete spectrum intercepted with minus infinity until L is a finite set. So we have only a finite number of eigenvalues when we look to the interval minus infinity L. So, as I said before, the essential spectrum is completely determined by the asymptotic behavior of the function v at infinity. Since we asked that condition of that limit on infinity. And eigenvalues can only accumulate at or above this number L. So now we have the description of the spectrum of the operator, and now we can talk about the composition of the space HS. So we want to use functional calculus to decompose this space into subspaces associated with positive and negative parts of the spectrum of the operator. What we want to do is to apply a linking theorem due to Maya and Soares, and that linking theorem is applied to strongly indefinite problems. And so we have to decompose this space, the space where we are going to set our problem. We have to decompose it in a way to apply this linking theorem. So we construct this operator, identifies the domain of this operator with the Sobolev space HS, and we prove an equivalence between norms of this operator and the norm of the HS space. So we know that prove that this operator SS is self-adjoint, and the spectral theorem for self-adjoint operators gives us that SS can be written like this, where E is a spectrum feature. And via functional calculus, we define the square root of this operator in this sense. Also as we have that AS is a self-adjoint operator, therefore closed, which possesses this domain here, where the functions on L2 such that this integral is finite. Some key properties is that I call it H, this domain, is a Hilbert space when we put an inner product on this space like this, and this is called the graph norm of the function U, which is given by this, and we also can write this norm like this here. Okay, the important here is that we want to decompose the domain of the space into these three parts here, which this decomposition is an orthogonal decomposition, where this E plus is P plus on the domain, E minus is P minus on the domain, and E0 is P0 on the domain, where these are orthogonal projections. We can show that these three spaces are invariant under the action of the operator AS. And so we can, with a sequence of lemmas, we can to show that, in fact, the domain of the operator coincides with the fractional subleft space agents. The idea of the proof is to define an auxiliary norm, which we call norm M, using the spectrum measure. So we define this like this here, where minus M, so we have an M here, minus M is the infimum of the operator. We show this relation. So this norm on this graph norm, H here, is equivalent to this norm M, and we show that this norm M is equivalent to the norm on the subleft space, and so we have the equivalence between these two norms here. And we conclude by density that, in fact, the domain of the operator is the subleft space agents. Now, this is the important norm that we are going to use. So we define, I call it norm X on this space as the square root of this sum here, where P plus, P minus, and P0 are those projections that I said before. And we can show that this norm X is equivalent to this norm H. And so, since we had that this norm H is equivalent to the HS norm, we have that the norm X is equivalent to the norm on the subleft space HS. This is important. This is what we are going to use to write our function, as I said here. So it's used on the spectrum decomposition and will be fundamental to prove the existence of solution. I put, it's really fast. We have a trivial inequality here, so we want to show this equivalence. We have that this is trivial. And for the reverse inequality, we have to consider two cases. So, first one is that 0 is on the spectrum is not on the spectrum of the operator. Then we have that AS, the operator AS minus 1 is bounded, and easy computations shows us this, and we also can show this one here. So we have indeed that what we wanted. The second case is when 0 is on the discrete spectrum of the operator. 0 cannot be on the central spectrum of the operator. So we only have to consider the case where 0 can be on the discrete spectrum. So we consider it not when it's not on the spectrum, and if it's on the spectrum, it can only be on the discrete spectrum of the operator. Then we have that the dimension of that space is 0, is finite, and only 0 when AS is restricted to A0, since A0 is finite dimension. This is continuous, and so we have this inequality here. When we look for this space E plus and E minus, we restrict our operator to E plus plus E minus. This is self-adjoint and injective, and so 0 is not on the spectrum of this restricted operator. Hence we have that this is bounded, and we can make some easy computations again to show that this works. And so if we combine these two cases, we have in fact the equivalence between the norms for all U on HS. Am I talking too fast? It's okay. Some consequences. E minus and E0 are finite dimensional. So by hypothesis V1 and V2, and using the finiteness of eigenvalues below that limit. And so we consider this E plus as the orthogonal complement of this E minus plus E0. And we call E1 as E plus and E2 as the sum of E0 with E minus. So we made our work, which is to split the space into these two spaces. I have a note is that this, as I said, this space is finite dimension from our construction. The linking theorem due to Maya and Soares can work when we split the space into two infinite dimensional spaces. So we are using a stronger, maybe could use any other linking theorem that could work when we split the space into a finite dimension and an infinite dimension space. But it works here for us. And the important, as I said, is this identity here. And so, so we have this equality here from the norm equivalence that we showed before. Thus, we can write the energy functional associated with our equation like this. And this means this part here, this quadratic part written like this, means that the problem is strongly indefinite, which means that it is unbounded from above and below. So we cannot use, for instance, a mountain pass theorem. It's not possible. We also have some estimates on this space E1 here, which are this infimum taken on the functions on E1 is greater or equal than that sigma plus. I will come back to it later. And this is positive. And also if we consider A0 as this infimum here, then A0 is positive and greater than this quotient here. And also we can show that the norm is greater or equal than this here for every u on that infinite dimensional space E1. So what we did so far is to decompose the space, and this gives us a natural framework to express our operator on the linking theorem that is the last part of the work. This A0 controls the coercivity on E1. We call it that A0 is this. We also have some compactness properties from the finite dimensional space E2. So maybe if E2 was infinite dimension, had infinite dimension, we had to make another approach. So this is not. So maybe this is not so easy. And this condition A, which I will talk later, A greater than this is A0 is needed for the linking theorem, the linking geometry that we are going to use in a few moments. So let's go to our problem. Again, we have these conditions. Okay, maybe everybody remembers these conditions. The important, what we did so far, is about the potential. So the potential is continuous, possesses limit at infinity. Zero is on this spectral gap. Now, what we mean by asymptotically linear, right? We said asymptotically linear fractional is from this condition here. As I said before, from this condition here. We're calling that f is the integral of this, capital F is the integral of this function f. What we have is that indeed this limit is plus infinity, and so we can apply the L'Hopital rule here, and we obtain that this a over 2 is in fact this limit here. And so we have that this limit here is a, which justifies the name asymptotically linear problem. Just to recall, I'll go very fast here, we consider this operator, and from what we did before, we have these two things happening. So the essential spectrum is on this interval, and the spectrum is on this interval here. I think this is it. So as I said before, we are looking for critical points of this functional here, which is associated with our equation. So this is the functional associated with the equation. And we have written this quadratic part of the functional on this way. And so let's talk about the linking structure of the problem. So if we have a Hilbert space such that we have subspace Z1 and E2 satisfying this condition here, which we already have made, and P1 and P2 projections into these spaces. Moreover, given a mapping defined on this way, we denote this phi Tu as phi Tu. We also denote this set, we define this set of functions where Wt is a compact operator. Also, by a Hilbert manifold of class CQ, we mean a closed subset of this Hilbert space such that we can find a function of class CQ where O is an open subset of our Hilbert space such that we can write M as the inverse image of this C. And if we consider two Hilbert manifolds on this Hilbert space, this denotes the boundary of the manifold Q. We say that S and the boundary of the manifold Q are linking whenever we have that phi on this set of functions, and we have this happening, that this intersection is empty for all t. It follows that this intersection is never empty for all t on this. So I have a picture here, which was made by another master student. We consider E as E1 plus E2, where E1, E2 is here, E1 is here, S is E1 plus Q, and Q is this intersection here, is the ball here. So we have, it was proved in this paper of 1979 by Benjamin Binovitz that these two manifolds are linked. Now I have to define what is a Cherami sequence and the set of functions. If I have a C1 functional, we say that a sequence on this Hilbert space is a Cherami sequence if the supremum is finite and we have this limit as 0. And if this sequence goes to C, we say that this is a Cherami sequence at level C. I think I won't talk about all these conditions, but we define the set of functions gamma satisfying all these conditions here, like this. So instead of enunciating the linking theorem, which is a big enunciate, I will prove the parts. I have to prove four things to apply the linking theorem. And I will make the sketch of the proof of each part, and define why the consequence of the theorem. So we have E, a Hilbert space, E1, a closed subspace of E, and E2 is the orthogonal complement of E1, and we consider I as a C1 function. So about the space of our functional, we are done, right? We had already made this here. We already made this here before. First of all, we have to prove that we can write the functional as this sum here for U on this sum, considered as U1 plus U2, with L of U as L1 U1 plus L2 U2, where this Li is a linear, bounded, and self-adjoint operator. So the idea of the proof, we almost already made it. So we take L1 as this, L2 as this, and then we have that L is, and take L as L1 plus L2. For U on this space, we write U like this, U1 on that space E1 that we constructed before, U2 on that space E2 that we constructed before, and it's easy to show this and this, and using norm equivalence, we have that this inner product here is indeed this integral here. And we consider B as this other part of the functional, so in fact we can write the functional on this way. For the second part, the second hypothesis that we have to show is that that part B here is weakly continuous and uniformly differentiable on bounded subsets of V. As I said here, this is a sequence of rather technical lemmas, so I won't put them here. One of the important parts here is the behavior of F and capital F. Under those conditions, F1 and F2, the F and capital F behave like this. It satisfies these four properties. This is easy to show. The difficult part is our dilemmas. For this, the condition E3 says that we have to show this. So we can find Hilbert manifolds with Q bounded and with this boundary. And these constants, alpha and W, and V on that space E2, such that these three things hold. So this is why we have to show that we have to define what are S and boundary of Q link. Again, we have much technical lemmas, and an important part is also that these two manifolds, Q like this and S like this, are linking. The boundary of this Q and S are linking. This is also on this paper by Bench and Rabinovitz, and unfortunately we had to put another hypothesis to show this, is that 0 is not on the spectrum of the operator. And finally, we have to show that if we have C defined like this, where lambda is this set of functions, I won't enter on the details, and if we have a sequence, the importance is to talk about this sequence here. If we have a sequence, if for a sequence there is a constant B such that UN belongs to the inverse image of the functional of this interval by this functional, and this limit is 0, then we have to show that this is a bounded sequence in E. So we consider UN a sequence here, such that we can find a B satisfying all these things here, and we assume that UN is unbounded. This implies that UN, we can find a subsequence such that this norm goes to infinity, and since this is a compact interval, we obtain another subsequence, a subsequence of this subsequence that satisfies this condition here for some D on this interval. This sequence is a theorem sequence at level D, and it's possible to show that this is a bounded sequence. We repeat this argument and we obtain infinitely many bounded subsequences of this subsequence UNK. And so the sequence must be bounded, and this is a contradiction with this. And so the conclusion is that the conclusion of the linking theorem is that if the functional is defined like this, satisfies I1, I2, I3, I4, then we have that the functional has a critical value. And this is exactly what we have shown. So the main reference of this work is this paper by Rabinovitz, as I mentioned before. the paper by Liliane Maia and Mayra Soares that I mentioned before. This is the submitted paper, and I put it here that we also made the spectral decomposition of the space H1 using similar techniques, but on this case, on this chapter, we haven't applied it to a problem, to any differential equation.
Any questions or comments? I have one question. I saw that all the construction made using L2, that's a Hilbert space. So is that possible to like generalize in another type of spaces, or you need the property of the L2 space? Because usually you have that Hilbert, and then you have a inner product, and then you have all those things. So is that possible to extend, or would be that difficult?
I'm not sure about the answer, but I think it's not possible to work in a space that's not a Hilbert space. Yeah.
Okay. Any other questions or comments? Okay, if not, so let's thank the speaker again. Also, I would like to thank all the speakers of today. Yeah, it was a very full day. And I have just two announcements. Tomorrow we will start a little later, so we start at 8:45. We organized the schedule in order to be able to rest a little more tomorrow morning. And tonight, as all you know, we have the welcome reception. It is scheduled to 7:30, but I asked them if they could put that earlier, so they said that's okay, they could start earlier. So if you want, we can go directly from here, but of course, if you prefer go to the hotel, you can go, but it's the same place that we had the lunch today. Yeah, exactly the same place. It's very close to the hotel. The name is Aduni Campi. I sent an email with the address, so it's very close here. And yeah, so I hope to see you all in a while.
Well, we're leaving right now, right?
Yeah, the ones that want to go directly,